Final day. I hope that you enjoyed yesterday evening and you could safely return to Rome for those taking the train or not. So today, we'll start with a deep dive on the different, let's say, model offered by ESA and NASA. So there will be a bit of deep dive on the Prithvi suite. There will be also some discussion, some presentation of the EVE project that we are connecting also within ESA, and also the TerraMine that was recently released together in between ESA and IBM. Then later on, there will be a bit of talk, invited presentation about infrastructure, so what we can expect next in terms of HPC, quantum, and stuff like that. And some wrap up, and then this afternoon we'll move to the hands-on session for those that subscribe to it. And so starting with this morning, so this deep dive, there will be 3 talks of about 30 minutes. The first one will be about Prithvi suite, so WNC, within climate, the Prithvi EO, then we'll move to the TerraMine, and at the end we'll move to more like LLM foundation model, so with EVE and also the Indus with NASA folks. So then I invite on stage the first speaker, who is Sajid from NASA. Over to you.
So hey guys, good morning. So I hope everybody is ready for the 30 minutes presentation back to back. Yeah, I hope you all had coffee from the cafeteria probably, so that you're awake. But yeah, let's go with the first part of the Prithvi. I think everybody here is well aware of what Prithvi models are and the foundation model are. So we'll go with a bit technical details later on, which we'll be doing in the afternoon session with the hands-on with Prithvi EO as well as WXC in fine-tuning. So if you have questions, if it is something very technical, you can ask, or you can also hold it for the workshop, which is for the hands-on, where you can go a bit more technical and fine-tuning style. So this work has been done with NASA, IBM, and a couple of other collaborators that we'll see at the end. But I'm representing here, NASA primarily, and also IBM. My partners are sitting right here in the crowd. So we have the first model, which is Prithvi EO, and this is the geospatial foundation model that we released last year in December, which was on December 4th. So the Prithvi EO model has been trained on HLS dataset, and this is from one of the collection from the petabytes of data that NASA has been collecting through multiple satellites. And HLS is one of the most used product from there. So this Prithvi geospatial foundation model, we had 2 versions of it. The first one was released in 2022, yeah, 2023, right? Yeah, 2023, and where we trained it on the US CONUS region for 1 year of data set from 2017. And so that was sort of a water testing territory for us, that what works, what doesn't work. And then we extended that further with our newer model, which we released on December 4th, where we trained on HLS for the last complete full set of HLS data, which we get from 2015, 2016 till now, and which is on the 30 meters resolution. We tested it on multiple downstream use cases, which we'll discuss down the line. And so this is sort of an foundation model fine-tuning, from pre-training to fine-tuning suite that you're looking at. So initially you have the pre-training strategy, which is you do the sampling, and we do the filtering and pre-processing, and then you have the SSL way of training the model, which is through the mask autoencoder approaches here, and then you try to do the reconstruction loss. So that's what the pre-training objective here looks like, which is the reconstruction. Then you take the same encoder and you try to fine-tune it towards the multiple downstream use cases, which can be, which you will be able to do that with a lesser number of labeled data that is required, right? And the same thing can be done operationally through the inferences. So a couple of our downstream use cases have been is being used by NASA for inferencing. Right now, NASA Earth data, that is like burn scar and other further data discovery. So a little bit about HLS. I think you guys might be knowing what HLS is, much better than me probably. I'm a computer scientist, not a remote sensing guy, but I'll take an attempt. So HLS is the product that is by NASA, which is a combination of the Landsat and Sentinel. Harmonized product, a 30-meter resolution. So it has, since you harmonize it, you lower down the complete rotation, circling down the Earth, which is to 2 to 3 days approximate period. So when you look at this whole data volume, so you're looking at a whole data volume coming from 2015 till now, and every 2-3 days. So the problem comes that how do you train such a model with so many data? Will that model understand the changes that is happening over the Earth? Because the change that is happening over the Earth is far lesser compared to the change that is not happening over the Earth. So it will create a bias toward the learning scenarios. So we got the whole data set collection, and which will go ahead with the pre-processing and pre-training strategies here. So firstly, we selected the high-quality data set, and which we use for the training and validation. So we minimize the cloud coverage, select the samples which had lower cloud coverage, which is less than 15%, and also got rid of the no data value, which is none actually for the 5%. We also try to represent the diverse land use and ecosystems. So sampling, which we did, was based on the entropy for the LULC, and which was separate, which was for the period going from 4 weeks approximately to 6 months, so that you can incorporate as many changes as possible into the model for the learning scenario. So this is overall a visualization for a couple of tiles from the training and fine-tuning samples, training and validation samples, which is distributed over the multiple ecoregions and to the multiple temporal regions on the HLS data. This was for 1 year samples distribution, which you visualize. So this is the same visualization we look from the perspective of training and validation samples that we got from 2014 to 2024. And on the right-hand side, what you look at is the weeks between the timestamps. So you can easily look at that the samples were forcibly here. In this version of the model, we made sure that the samples, the temporal samples are minimum 3 to 4 weeks to a maximum of 6 months apart, so that we can force the model to learn the seasonal to subseasonal changes or learn the temporal changes that is happening over the Earth. Contrary to the previous version that we released, where we had 3 consecutive samples, which was actually 2 to 3 days continuous in nature. So this is the Prithvi pre-training architecture that we are looking at. So you have input images, and then you have the spectral bank. I think here everybody is well aware of the foundation model and different architecture, so we'll keep it a bit short, but yeah, feel free to ask us any questions if you have. So you have the spectral band, and then what you do is you mask out 75% of that input, and then you ask the model to reconstruct that. Added on that, we added the 3D patch and positional embedding, so we also have like 4 input time steps as we talked about. But those input time steps are 2D in nature. So when you try to do the positional embedding, you can actually go beyond 4 input time steps for fine-tuning fine-tuning downstream use cases. So you're not limited by the part that you require always 4 input time steps for fine-tuning. You can go for 10 input time steps for fine-tuning. You can go for lesser than 4 as well. And then what you did minimization is on the reconstruction loss with the 75% of the mass that the model was able to recreate. So the data that you're looking at is approximately 3,000 plus tiles covering approximately 60% of all urban regions from 2015 to 2023. We had approximately 4.2 million samples for training with a sample size of 224 by 224 cross 6 cross 3, 4 actually. So 45,568 samples were used for validation. We did with a couple of trainings. So we had trained on ULIC supercomputing, as well as we tried a couple of things on the NAS. So on the ULIC supercomputing, the whole model was pre-trained, where we used, we had A100 with 40 GB memory, and we used 4 GB per node, 4 GPU per node was the design of the system. So for the first pre-training, we used approximately 80 GPUs, which are 20 nodes, and it ran approximately for 11 days. So we released 2 versions of the model, 300 million and 600 million parameter model, which comes with temporal and location embedding and without as well. So you can choose what you want to use, which can be pretty well for looking at validation and embedding space, where the model doesn't understand the temporal location context, but still able to understand how the samples cluster together in the embedding space. The model is open source. This is the Hugging Face link. You can go to our IBM NASA Geospatial Hugging Face page. You can download all the previous model as well as newer model as well from both EO and WXA. This is what a loss curves look like, but you can look at from the Prithvi large to Prithvi huge, which is 300 million to 600 million parameter. Approximate training time was 11 days to 10 days, with the number of GPUs to be 80 GPUs with, compared to the 240 GPUs. We trained the model, and then we validated the model on multiple downstream use cases. So for the downstream use cases, we went on the partnership with the different institutions where they provided the data samples as well as the fine-tuning, hand-level data for fine-tuning exercise. And this was a collaborative effort for letting the SME do the fine-tuning themselves, so that at the end it's like sort of a training as well for them, and then they can pass on the knowledge to their people, right? So like we had the burn scar detection that came from NAS, and then floodwater delineation. We had the landslide from the Arizona State University, crop classification from Clark, and then with the burn intensity from the NASA different division. We had a regression for the GPP flux and AD covariance that came from the UC Berkeley, as well as the generative for the cloud gap imputation, which was also done with the previous version actually with the Clark University. There are other downstream use cases as well, but in the interest of time, I just kept a couple of them, and we will pass through that. You can easily go back to our paper and look at all the results that we have got. So this is what an architecture looks like for a fine-tuning of a standard fine-tuning for burn scar flood mapping. This can be summed up in pretty well with the TerraTorch pipeline that you guys will be doing it hands-on today. But if you want to just use the Prithvi encoder yourself and design a different sort of architecture for fine-tuning, you can use that. You can do that as well. But today, I think this is all has been handled pretty well by IBM by using TerraTorch. So you just import the model from there and you just perform the fine-tuning for your task. So what you do is you take the encoder, you have the upsampling layers, you perform the convolution, and you update based on the ground truth. So this is what we did for the burn scar as well as flood mapping. In a couple of cases, you have the 30-meter product as well as the 10-meter product. Model worked on both of the situations. This is for the burn intensity and the crop classification. You have almost same thing. It's just the regression. Here you're looking at regression and segmentation, multi-label segmentation. So something very similar, but it's a bit temporal in nature. You used, in the initial condition, we were using 3 input time steps to see how the model behaves when you're feeding the temporal information there. So we also tested on the GeoBench dataset performance with the different models and what the performance looks like. The model performed really well, even on the samples which were not at 30-meter resolution, which were actually at the finer resolutions, like 1 meter or 3 meter. And then we saw improvement compared to our previous model that we released, 100 million, and compared to other models as well, which was out there. Here are a couple of results for the Sen1 flood dataset and then wildfire fire mapping. You can look at from the 100 million and 300 million parameter model from the temporal and location embedding. We see that the model performs a bit better when you're feeding the information to temporal and location embedding, and also the size did matter a bit. So when you increase the number of parameters from 300 to 600 million parameters, the model improved in performance a bit. We are still going ahead with training a billion parameter model. We'll see how the performance looks like, and when we release it on our IBM NASA Geospatial page. Same thing that we look for the wild scar fire mapping results, and the same thing that you're looking at here in terms of the results for the compared to 100 million, 300 million parameter models, and 600. Here are a couple of visualization for you to digest for the flood mapping. Same, you're looking at the true color composite, ground truth mask, and predictor mask from the model itself. Here you're looking at the visualization for the burn scar mapping when you feed the true color composite compared to the ground truth mask compared to the predictor mask from the model itself. Here are a couple of results with the landslide detection, which was the newer downstream compared to the version 1 that we did, and we compared it with the baseline approaches. Also, this was a competition data set that was used from Landside for Sense, and we compared with the UNet plus as well with the backbone of ResNet 50, and compared with the Prithvi EO 2.0 600 million parameter model. Here we did not use the temporal and location embedding. The model performed a bit better with 600 million parameter model. We changed the loss function to LOAS as well as the mixing with the cross entropy here. Similarly, we tried on the just 10% and 1% of the data for the fine tuning. So the first one that you're looking at is actually looking at approximately 100% of the data for fine tuning. But what we did was we threw away 90% of the data for the fine tuning, and we just tested on what happens to the model and performance if you just feed the 10% of label data. And there also, the model performed really well with just 10% of the data, which was really good. We did some more analysis on, which is a thorough analysis, which you can find in the paper, that even by reducing the data a lot, the model performs really well. You can also see in the terms of performance with the number of iterations that you're doing. So when you're using a foundation model for fine-tuning, to a specific task, number of iterations required for reaching the optimal performance is lesser than by the baseline model that you try to train. So this is with the another Cenfor map, which was done by Ulick for classification and fine-tuning based on the EO 600 million parameter model and 300 million parameter model with the VIVIT model as well with the baseline. Here is a couple of results with the 10% label training data. So this is with the other downstream tasks that we looked at, which was for the burn scar, flood, and crop. What happens when we try to use an adapter with it? So rather than use just fine-tune with full model, what happens if you use PEFT or low-rank adaptation? In that case, do you see improved performance, or do you see, you're dealing with a less number of data set as well? So in this case, we are using low-rank adaptation for comparison, and where we are training it on just 2% of the parameters of data, as well as 10%. So if you're looking at 300 million parameter model, you are just training on 600,000 of the parameter after that, or fine-tuning. So it can actually fit on your laptop and on GPU, and you can work with that one as well. We tried with a different adapter mechanism as well, which we are still trying to look at from the injection point of view, that what happens if a data set is there, which model has never seen before. How will that model behave to that data? For example, SAR data set or something else. Can I inject that information into the model itself and perform and leverage the information that is present before that? Visualization for the crop classification that we are looking at after the, for the true color composite and from the models here. This was a bit of a different task that we are looking for the GPP flux one, and this was from the UC Berkeley for the flux towers. Now, why this is a bit different task is here, because here the model was trained on HLS data set, right? But we tested this model on a multimodality scenario, right? So what is happening here is we are feeding the HLS images, which is of a 50 by 50 sample tile size, and then we are also feeding the 10 meta2 variables here. Now, meta2 is a reanalysis data set from NASA for the atmospheric variables, right? So you're feeding that, and what you're doing is you're just concatenating the features and getting the output from the model for the regression of the flux one. Here also, the model performed really well compared to the standard baseline that they had with the SME selection of their different test site. We are extending this across the full US region now in order to test it. So in a nutshell, in summary, since I have to move to the next part of the presentation as well, which is on the WXC. So we trained a geospatial foundation model Prithvi on the global HLS V2 dataset. We had the sampling strategy was based on LULC and temporal condition of 4. And we had used 300 million parameter model, and we have 600 million parameter model with temporal and location embedding. We have evaluated in our multiple downstream tasks related to the specific downstream tasks like burn scar, floodwater delineation, landslide, crop classification, burn intensity, GPP flux, cloud gap generations. But also we have tested it on the benchmark data sets with that as well. And then also we have tested the model with as low as 10% of the data, as well as the 1% of the fine-tuning data, and how the performance looks like on that part. Cool, so here are the QR code for the model and data set, as well as for the paper. So if you guys want to take a picture, I can hold it for 10 seconds, and then you can refer to the paper, but we will be going for the deep dive into the next workshop session, which is post-lunch, on using these models and fine-tuning for a couple of tasks on that one. So thanks to all the partners here. There are a lot of logos. I hope I'm not missing anybody. So we had obviously NASA Impact IBM, and then Ulick Supercomputing for the training of the model and the support they provided. Clark, UH, then we had the Arizona State University, as well as the MAPAR and the USRA for the collaboration. Oh, I'm missing the Berkeley logo here. So thanks to UC Berkeley as well. Cool. So now we switch gears to our second foundation model, which is the Prithvi WXC, Weather and Climate Foundation Model, right? So we looked at the EO model here, and then we are looking at now the Weather and Climate Foundation Model, which is bigger in size and a bit different architecture to train with. So there have been major two revolutions in AI, and that has been, looking at how you predict the forecasting emulators like GraphCast, ForecastNet, and other stuff. And then there have been foundation models like, for example, we have recently seen Aurora, and then initially it was at 1 degree you had the Climax and other stuff as well. So it's a very simple task that you get a huge speed up that ForecastNet actually proved it from that scenario. And the future is obviously that you're going forward, HPC and AI hybrid approaches will be the part of the toolbox, and you can use it for multiple situations, for multiple use cases, recovery of missing information, and efficient formulation of the physical processes. So atmospheric processes happen at multiple different scales, right? So you can look at the bottom right, the temporal scales of the different events that we were trying to initially model it on. But it's very difficult to have one model to do everything, right? So we decided the gray area where we will work on the terms of the temporal and spatial scale and design a model for that. So the challenges for the forecasting was the atmospheric phenomena occur at many scales, and the training data sets limits and scopes. So the computational power obviously limit the grid resolution, and we have to resolve the processes. So we have majorly two revolutions in AI, that we have the AI rapid forecasting models that we have seen, a lot of them like GraphCast, Pangu, ForecastNet, GenCast, and other stuff. And other foundation models like Climax, Aurora as well, for which are used multiple different data sets, as well as for the multiple downstream use cases they have shown. So when we designed this Prithvi WXC model, the objective was not to just do the forecasting, right? Forecasting could have been a one downstream task, but we wanted to design a model which can be used by the atmospheric scientists in their own experimentations and for the simulations. Forecasting can be one of the goals, but was not the goal from the NASA point of view. So the foundation model for weather and climate sit at the intersection, and it is a bit I will not say now it is underexplored, but still it is underexplored from many phenomena because you have a lot of non-stationarity in the atmosphere, and we are still looking at the same one modality, which is from the reanalysis data sets only. We are still not merging the land surface interaction or land area interaction sort of data sets. So initially we had one objective, to design a trained foundation model for weather that can easily be adapted for multiple use cases. So we had the Prithvi WXC model, which was built on 160 atmospheric variables from the NASA's MERA-2 datasets. And the key application testing that we did on the autoregressive rollout forecasting, we did it for downscaling, we did it for gravity wave flux parameterization, so which was feed into the climate model, and then extreme events estimation like hurricane and other stuff. What you see on the right is the first attempt that we did before designing the foundation model. So this was one of the papers that I submitted to ICLR, which was on Clifford neural operator. So trying to prove to the atmospheric physicists that model can learn physics. So in this model, the simulation is just for the shallow water equation, which is being learned from the MERA-2 dataset, which is through the U10, V10, and SLP, and trying to do a forecast for the next 4 days based on just 3 variables, trying to solve the shallow water equation based on Clifford neural operator. So there are a lot of data sets out there, right? So we have them, but we decided to use the MERA-2 data set, which is at 0.5 degree resolution, and these are the pressure levels variables and surface variables that you're looking at. So through all this whole Pandora's of variables to fine-tune them, to train the model on, we selected 60 variables, which starts from 1980 till present date. So you get the MERA-2, and it is at the 3-hour temporal resolution. The spatial resolution, as I discussed, is 0.5 to 0.625 degree. And we have also atmospheric data and static variables that we'll go through about. So here are the list of surface variables, vertical level variables, and static variables that we used in the model. I don't expect you to remember all of this, but yeah, definitely you can go through the paper that we have, and you can look at the variables that we have used for training the model. So surface variables, here you're also looking at the nominal pressure levels that we have used. Now, these pressure levels are the model levels that we get from the MERA-2 dataset. This can be converted to the pressure level that generally atmospheric scientists try to work on. So for the pre-training objective, right? So here we were in a bit of fix. What should be the better pre-training task for the model? What do? We have seen generally the foundation model being trained in the masking approaches, but then the masking it will learn a lot of spatial distribution and correlation between the data and how it's dissolved in that space, but can that also regress over time is a major question. So we did the forecasting and the for the mask autoencoder approaches that we have seen in the previous papers, right? And also in the Prithvi EO that what we used. So obviously, when you do masking, you have majorly, you can do one thing is you can reduce the memory load. Since you're looking at a 160 variables of Meta2 data set across, if you want to feed 2 input time steps and try to do autoregressive rollout for 2 or 3, you will be going out of the 80 GB GPU memory, right? Which we trained on a NAS, which was A100 80 GB. So we adapted to multiple techniques of engineering there as well, which is FSDP and other stuff. But still, when you use masking, you can lower down the memory pressure a lot from the GPU. And you can also avoid using additional tokens, right? So this is the fundamental base architecture that we actually thought of for designing for the Prithvi, and which is right now, which is working. So it takes in the surface data, which is from the, which is time, latitude, longitude, as well as the vertical data, different things. You have the surface climate variables that you calculate from the climatology, as well as the static inputs and the context information. You do the tokenization, you do the masking, which is 50%, and then also you do later on the autoregressive rollout, which we'll see in the coming slides. The key feature was that this became a grid-free model. It can be used for both Euclidean and spherical topologies. We had the encoder, decoder, which were fully attention-based, and all auxiliary tokens like lead time and other stuff was injected by the contextual tokens. We had 2 input time steps into the model, and the pretext task was a combination of the masking as well as forecasting. So given the mask of 20%, you ask the model to give me the 12 hours ahead of the, of the current state. So going a bit more into the architecture here of the model, what you're looking at is initially there are 2 stages of training. So in the phase 1 of training, we did a masking ratio of 50% with a drop path of 5%. We had the alternating between the local and global masking for the gradient descent steps. We did a random forecasting steps, which was oscillating between 0, 6, 12, and 24. It was not very fixed in nature. Then we have the random input delta, which we are choosing for how many input time steps to feed and what should be the variation of those input time steps, which goes from -3, -6, -9, and -12. We trained it on 64 A100 GPUs with a batch size of 1 with approximately 400,000 gradient descent steps. We tested this model on the downscaling gravity wave that we will be talking about, right? And in the phase 2, what we did was we changed the model is we changed the masking ratio to 0. So we keep the full input to the model. And then we added the swing shift to the decoder, and then we set the drop path also to 0. But what we did is we did a fixed forecast lead time and input delta to 6 with no randomization. And then we tuned it with multiple autoregressive steps, which is 1, 2, and 3, depending on the 16 to 48 GPUs. What do I mean by autoregressive rollout steps tuning here is what you do is you feed in 2 input time steps, you get the next output time step, you take that output time step, which model has predicted, feed it back to the model, get next time step, and then you minimize on the combination of the losses that you get from the ground truth versus the model prediction. What you see here is the loss function update here, so which is based on based on climatology and the standard deviation from the ground truth. Here are a couple of zero-shot validation results from the model. So reconstruction performance of Prithvi, which was evaluated with different percentages of masking, so 50%, 60%, even at 99% of masking. What happens if you just mask 99% of data and feed just 1% of data to the model? What will the model produce? So the model performance was really good, even with the zero-shot for the rollout situation, which you can look here in terms of number of days. It explodes later on in terms of RMSE, but that is tend to happen. If it not go bad in RMSE, it's certain days, then I think there is something problem with the model. Here are the zero-shot validation that we tested with the event prediction like hurricane, which we look on the left and top left, which is the hurricane Ida, the ground truth, and the weather and climate, so the Prithvi model prediction, which is very concurrent with the track forecasting, so it follows the track of the model. There was some error in the terms of the intensity, but that is existing with all of the other models out there as well. So there is a couple of approaches that we try to correct the track and intensity with the raw data feeding in. I don't know if you have attended a couple of other poster sessions, then there was one poster which was actually talking about how we use raw data to feed into the Prithvi WXC to correct the track and the intensity of the hurricane as well, which is more accurate. But here we compared it with the ForecastNet, which was released by NVIDIA, and we did fairly well against that. So other downscaling validation. So we had another one, which was the downscaling validation. I will not go pretty deep into this, but yeah, you can you can actually look at in the paper, and we will be discussing that probably in the session as well. So we tried on the Meta 2 as well on the Cortex data set from 12x to coming down to as low as the Meta 2 resolution, which is 6x coarser. So this is the fundamental architecture that we were using. So you go the down sample, you'd use the Prithvi WXC encoder with a couple of skip connections, and you go up sample again. So this is the gravity wave flux parameterization. And now this is a bit of a unique task as well. Here, the reason was that this model was not designed for, which you think from the resolution point of view, spatial resolution. The model was looking at a 50-kilometer grid scale, right? But what happens if I actually feed the model something as coarse as like ERA5 or ERA5 scale up to 200-kilometer resolution? How does the model behave? Will the model blow? Will it collapse? Will it provide me some output or something else? So we try to do for the parameterization. So this parameterization calculator for the gravity wave will feed into the climate model. So basically, you're just calculating a functional mapping here. So based on UV temperature and pressure, you calculate a U prime omega prime and V prime omega prime, a mapping function which have been through the physics-based approaches. So what you do here, and you're dealing with 488 variables, right? Now, just going back a bit, Prithvi WXC was trained on 160 variables, right? So how do you fine-tune on 488 variables, Sujit? So it's like, so what we did was, and this 488 variables was just the UVTP at 122 pressure levels from Meta 2, came to at a higher resolution. So what we did was we actually let go of the patch and position embedding, and then we just take the encoder, we froze the encoder, and then we added a couple of convolutions block beforehand, a couple of convolution back after that, and we added a couple of skip connections. We traversed the model through the convolution blocks to hit the encoder at the embedding dimension that we were feeding at 2560 for the 2.3 billion parameters, but we take it down upsampling again to map it to U prime omega prime. We tested this approach, and in comparison with a unit as well as the attention unit. So just unit would not have been a fair comparison because you're dealing with a lot of variables here. So we tried with attention unit, and we saw that the model converts really faster compared to Prithvi WXC. And also the parameters, the flux parameters that we got from the model for the gravity wave were fairly accurate. So right now, Stanford is continuing on this one, and they're trying to feed it to the Cambridge model. I think they're the climate model, which is here at Cambridge. So this was the whole team that worked behind the Prithvi WXC from IBM and then from NASA. I will not go through all of the names, but yeah. So that will be the thanks to NASA, Impact, IBM, Oak Ridge, Stanford, Colorado State, for all of this work. Here are the links to our GitHub for fine tuning. Also, the Hugging Face link for our model. So we have our 2 versions of model there, which is 2.3 billion parameter from the stage 1, which is without the rollout, and that's 2.3 billion parameter model with the rollout. Today, when we do this session, we will have a very smaller model which we created just for the sake of running it on the smaller GPU system. But if you want to use these models, you can use actually if you just try to do it for simple fine-tuning, you will require approximately 2 A100 80GB to fine-tune the model, or you can take the smaller model for fine-tuning the approaches. And also there is a paper. That would be it from my side. Open to any questions that you have. Otherwise, we'll see you in the hands-on session.
Well, maybe any quick question for Sujit? Maybe just one? Well, if not perfect, we are a bit late, so let's move to the next speaker. Thanks a lot, Sujit. It was very insightful. So now I invite on stage Thomas, Benedict, and Valerio. So Thomas and Benedict from IBM Research Europe, and Valerio from ESA Lab, and they will be giving a talk on Teramine, the IBM ESA foundation model. Over to you, guys.
Hi, everyone. Hi. Yeah, very nice to present Teramine finally. So it's a model we worked on for like a month, and it's nice to see it finally out since 2 weeks. And I already heard it sometimes in the last couple of days, so nice to present it today. So as Nicola already said, it's a shared presentation, so we will cover a bit the model architecture, evaluations, and how you can also apply it to a real-world use case. So first, let's have a look what Terramind actually does. So Terramind is a generative model. We have like a lot of different modalities and can actually predict other modalities from the input. So on the left side, we see some raw inputs, images from like Sentinel-2 and Sentinel-1, and we can use Terramind to generate other modalities like also S1, digital elevation, LULC, or NDVI. And of course, like these models, like these images are not perfect. It's more like mental images of the model and their understanding. But it's quite nice to see like the correlations between the different modalities and what the model can actually do and like the understanding the model has from satellite images. So let's have a look how we actually got to this result. And this looks a bit complicated, but we will break it down in the next slides. So on the left side, we basically have a lot of different modalities. We have an optical one from Sentinel-2, SAR data from Sentinel-1, elevation, and so on. And we actually use like different versions of the single modality. So for example, for S2, we have like 3 different versions. Just to make it basically easier for you guys, if you use the model, you can basically directly use the patch embedding for the correct version. And the model doesn't have to like learn from like S2 to, from like level 2 to level 1 and so on. Then we have different forms of tokenization. We have a simple patch embedding for raw inputs. We have some tokenization for the different modalities and sequence input, for example, for coordinates, so that the model also understands like geographic understanding. And based on this tokenization, we can basically then run some correlation learning within the token space. So it's just important that like we move everything into the token space, and then we can run easily correlation learning. Okay, so let's break these different steps down. And one important thing, so we trained a model for 5 billion tokens on the Jülich supercomputer, so similar supercomputer as we used for Prithvi as well. So yeah, let's break it down. The data, we actually generated a new data set for that. We call it TerraMesh. We also open source it next month. So if you guys want to use it, feel free to do that. And it's basically consisting of SSL for EO data and Major Tom data. And we basically subsampled it a bit to basically have a nice distribution with upsampled areas and so on. And we can see that it's quite consistent between the different modalities and different input types. And yeah, that's basically the basis we used for the correlation learning. The next step was to train tokenizers. So the idea here is that we don't use like a reconstruction task or like a typical reconstruction task we normally use for MAEs, but like more like a token prediction task, because like classification sometimes is a bit more stable than, for example, a regression. And that's why we tokenized all the inputs, and therefore we trained VQ VAEs. So that's basically an approach where you use an encoder which encodes an image, it predicts it into a token space, and then you use a quantization method. Specifically, we used finite state quantization, which basically maps every encoded patch into like a single token from a codebook. We specifically used a codebook size of roughly 15,000 tokens. And then you can basically encode a whole patch with like a single integer value, which is your token ID. And then for reconstruction during training of these tokenizers, you have some diffusion steps, which you see here on the right side. So we already heard something about diffusion in the last days, so I guess you guys know that or like can look it up. And that's also important for the generation of the model. So if we run generation later, we basically need these diffusion steps to get like nice generated images. And that's the whole idea for like preparing the actual correlation learning. And then in the correlation learning, we have like some small example here. How does it actually work? And just to be clear, like that's quite similar to what 4M does in the general computer vision domain. So they kind of introduced this idea. So we have on the left side some inputs. Here we see 4 different modalities. And we first sample some input tokens. So again, they could be from patch embeddings, from raw input, or they can be tokenized inputs. Also from sequence tokens. Then next, we also sample some target tokens. Here we use target sampling as well, just to make the pre-training a bit more efficient, because you don't need to input like 1,000 tokens. It's fine if you only need like 200 tokens the model has to predict. So these are, of course, like different tokens. And for the target prediction, we only use the tokenized versions, so with the VQ-VAEs, or the text tokenization, just because then we can basically use the classification task instead of the regression task. So now the actual task for the encoder is to basically generate a latent representation of the inputs so that the decoder can easily predict the target tokens. And then we can calculate the cross-entropy loss based on like these 15,000 classes kind of, which we have per modality. So in total, it's more like something like 90,000 classes we have that we are predicting basically. And that's basically it. So then you train that for like 500 billion tokens, and then you get a nice model, which we call TerraMind. So now overview again. Here we have like a lot of different modalities on the left side. The model basically natively supports all of them, either as raw inputs or as like tokenized inputs, and then the correlation learning, which basically generates this like good understanding of the different modalities and their correlations. And this model we can now use for different downstream applications. So one is, of course, multimodal generation, which I already showed. You can also use it for fine-tuning. So that's, I guess, like what we all do, mainly with the foundation models. And there's also like a new idea we had. We call it thinking in modalities, where you can basically improve fine-tuning by generating additional tokens with TerraMind. So we're going to have a look at that later. Okay, so first let's have a look at how any-to-any generation works. So here again we have some input, here an S2 image, and then we basically use TerraTorch to encode the information in this image, and we tell the decoder which modality we want to predict. So here, for example, we use S1 tokens. The model generates the predicted tokens, and then we use the diffusion decoder from the VQ-VAE to generate the output. And we see that the predicted, or like the generated images is quite nicely correlated. The nice thing here is now that we actually have like this predictions in the tokenized space, and we can just input these predictions again as an input to generate an additional modality. So now we have as input the raw S2 image and the generated S1 tokens, and we can run the same pipeline again. We encode everything with TerraMind and predict another modality, in this case them, to generate a second prediction or like generation kind of. And by this generation, we basically get this nicely aligned generations across all modalities. So if you check, for example, the predictions from the S2 input, then also S1, DEM, LULC, and so on are nicely aligned and consistent, so you don't have like variations between them. So that's a nice trick by this chain generations. The next idea we introduced with TerraMind is thinking in modalities. So in the top, you basically see a standard fine-tuning pipeline. You use the encoder from a foundation model, in this case TerraMind, and then you have a task-specific decoder. In this example, for example, like a segmentation decoder with like an UNet hat, and you have a generation, in this case, like I want to predict water and flooding. But you see that the model kind of like misses some points, generates too much water, because it may not understand well where the water is, so it has some difficulties. But now we can basically teach the model to first think about like another modality, in this case LULC. And in LULC we already have the water class encoded, right? So like if the model first think about like LULC, which it already was trained on in pre-training, it might be better in fine-tuning, and that's what we actually do. So we ask TerraMind to generate LULC tokens. Here we also visualize the generated input, but actually we now input the raw LULC map. We only input then the tokens from TerraMind into the actual downstream model. So you run TerraMind, generate some additional tokens, which is kind of like an internal representation of another modality. And then you run your encoder and your task decoder, which you actually fine-tune. So the TerraMind model is completely frozen. You don't have any expensive diffusion step, which makes it not super expensive to run it, and you get better outputs because the model basically has the additional information as the input. Okay, so that's all about how the model works, kind of. Now it's, of course, a big question, like how does it actually perform? And that's something Valerio will talk about.
So thanks, Benedict, and thanks, everyone. Yeah, basically the question is, okay, Terraman is very cool, but is it working also? And the answer, of course, is yes. How did we assess this? We used Pangea, so basically, maybe you already know about this because we talked about it in the past days, but basically we have a very diverse set of data set covering different tasks, different sensors, different resolution, and different domains. And then with this, we benchmark all the models already implemented in Pangea, and then we added also Terramine. If you want to just give a look to the comparison in this spidergram for Terramine with respect to other models, you can see that the best other models, you can see that basically for all the tasks, it looks like it is outperforming them. But then if you want to go more into details, there are even more cool stuff because, for example, Terramine is the very first model in Pangea that is outperforming in average also UNet. So if you focus to the graph at your left, you can see that in average for the MIOU, Terramine is even better than UNet, and we discussed a lot why UNet generally is still one of the best among all these models. But then we were also very happy about the other performances on other tasks. So for example, I'm considering downstream dataset in which, on which that we're using some sensors that were used also in the pre-training step of Terramine. So for example, Sentinel-2 with multispectral information. We observed that, in this case, it was MADOS. We observed that Terramine is really outperforming of more than 5 point of MIOU, the other model. This was very impressive because we observed that other models like pre-trained on Sentinel-2 like Chroma were doing better, yes, but not that better. Also compared to other models that were, for example, pre-trained on high-resolution data like JFM or remote clip. But what happens if, or for example, are using Terramine for dataset that are different, for example, on different sensors with respect to the Sentinel-2, Sentinel-1, and so on? Well, for the low-resolution one, so for example, HLS, Barnscars, that has also less multispectral information if compared to the Sentinel-2, because Barnscars just have 6 bands. Well, it is still among the best and is just falling behind UNet, that we already discussed why is generally the best, and Prithvi, that is the native model. I mean, in the sense that was pre-trained on HLS, so we were expecting this kind of performances. But also when considering high resolution datasets, so for example, in this case, it's 5 billion pixel, so GauF-N2 is RGB and near-infrared bands. We observed that, again, Terramine is doing a great job because it's just falling behind the dataset that were, the models that were pre-trained on very high resolution data. So in this case, remote clip, scale MAE, and so on. So from the discriminative task point of view, we were very happy about these results. Then, of course, we asked ourselves, okay, we really wanted to invest about multimodality because it's one of the pivotal elements in the new generation of foundation model. But is this effective, the multimodality trick that we're using in Terramine? And also in this case, the answer is yes. And so we took the dataset from Pangea again that are using multimodal data. So in this case, Sentinel-1 and Sentinel-2. And we observed that, yeah, basically when using both the modality, results are always better. Then other than that, we benchmarked also other aspects of Terramine. The first one, again, is thinking in modalities. That was very nice because basically can answer too many questions. For this framework, we use N1 floods, and so we use basically flood detection dataset and agricultural segmentation dataset. And we observed that, yeah, also in this case, generating new modality is very nice and is helping the model to learn. And this is, from our point of view, is very interesting because it's saying, again, not only that multimodality is helping, but also that synthetic data could be of help if they are generated in a good way with a high quality standard. And also, in this case, we can say again that we can assess the generation of the other modalities in Terramine is high quality. And finally, yeah, we also tried a few shot experiments, and the setup in this case was the one-shot 5-way. So I don't know if you're familiar with it, but basically we made 200 runs of one shot, just sampling for the labeled data, so among the, let's say, training data set, just 5 samples, 1 per each class. And then with this, with KNN, we just did the inference on the unlabeled data, so on the query set. So in this case, we are not touching a weight. We're not fine-tuning even a weight of our of our model, just to assess if the latent representation of it are powerful and effective. And again, in this case, we selected a few data sets. And we can observe that both for Eurosat, so land cover classification dataset, and for meter ML, so meta mapping classification dataset. So in this case, we're talking about classification. Terramine can work better independently of the data that we have in input. So in this case, and it was even more interesting to observe that, for example, in the case of NIPE, in the case of Matter ML, in which we can have higher resolution data or lower resolution data, the lower resolution data that were the one that we use, again, for the pre-training, were even performing better than when using the NIPE. But in any case, these results, if compared to other models that are well suited for this kind of downstream application, are working well. So yeah, going towards the end on this, what is the take-home message? Yeah, of course, Terramine is having good performances now already at the moment. So for example, on Pangea benchmark, it's outperforming most of the other models. It's working well on independently of the resolution of the dataset, independently of the domain of the dataset, and so on. And also, we can observe that the multimodal inputs are really useful, not just because it's adding more data, but because it's kind of, through the correlation learning, can really fill the gaps in the latent space. And this is true not just for the multimodal experiments in the discriminative task, but also in the generation step. So again, also in this case, I would like to say again that also generating high-quality synthetic data can be very helpful for the community, and this can be, of course, one of the tasks that Terramine can help solving. And yeah, and finally, what also we can say, of course, as you observed in the last set of experiments, that the embedding space of Terramine is already very rich. And then, of course, this is also just a starting point for many other applications. Now we will see some application that could be done also now, but we're also welcoming all the community to have more. And thanks.
Thank you, Valerio, for introducing the performance of Terramine. I'd like to give you here an example in a maritime use case. In particular, as you also showed that the MADOS benchmark Terramine performed extremely well. So we just want to make this a bit more visual. And maritime use cases are extremely important, as you all know, right? In particular, as many ships are not being tracked, illegal fishing going on, there can be oil spill risks, etc. So very important topic, and we would demo Terramine in operation in the IBM Geospatial Studio. So basically, this is the enterprise hardened platform to work in a no-code fashion with foundation models, including Terramine. So basically, you can upload annotations, you can fine-tune the models in a no-code environment, and also you can then run it in inference mode at scale. And here, the example. So basically, it's about using Terramine first with a single modality in the detection of ships around Ellis Island here in New York. So you can see if we only use S2 information, then we pick up some of the ships, as indicated here in green. So we miss quite some boats. Accordingly, the thinking in modalities helps. If we ask the model to generate additional land use, land cover tokens, as Benedict introduced in his slides. So that's kind of the, not a land use map we're using, but this is really the generated land use, land cover map from Terramine. We use those tokens as an input as well, and you can see that now the model picks up many more of the ships in the harbor. So this is extremely important. To pick up the activity in these areas. So we stack now a quarter of satellite images and can then identify the activities in the different harbors. So we looked at harbors in the US and identified Los Angeles to be a very active port, as you can see then in the temporal diagram there. So this is indicated by kind of trading numbers from the very port. So But then also, if we are thinking about maritime sanctuaries, so let's move to California. So we have the Channel Island National Park there. And here it's really about identifying activities and ships with respect to illegal fishing, but also kind of the risk of kind of putting the biohabitat in danger through oil spill or waste. So here again, we use TerraMind to identify ships, and we also translate now into SAR modalities. So we have the original Sentinel-2 image, as you can see on the left, and on the right side, this is a generated S1 image, and you can see it removes nicely the artifacts in the clouds, and the ship still is also be translated into the modality. So again, here we can then ask the question, what are the activities in the last quarter in this area, and in particular kind of close to the islands and in the perimeter of kind of the national habitat. So I hope these examples kind of demonstrated nicely kind of how the model thinking in modalities can help, and also kind of the any-to-any translation can be used. So yeah, and we're happy to announce that the model is available on the Hugging Face. So please download, interact, and use the model. This afternoon, there will be also a session where you can, together with the experts, explore the model. So take the opportunity. It's already fully integrated into TerraTorch. So basically, you can do the fine-tuning, the thinking modalities, and any-to-any generation just in TerraTorch. So, and finally, we are super excited to announce that we open up here the TerraMind Blue Sky Challenge. And so it's a bi-monthly award. So submissions, the first submissions we expect until end of June. You can win 1,000 euros. And we just want to see how you interact and how you're creative with using kind of these new capabilities of the TerraMind models. So just go wild and submit your applications and explorations. So we're really looking forward how the community is picking up the models. Thank you very much.
Any question? Yes. Just wait for the mic.
Thank you for the presentation. I have a couple of questions. I hope it's okay. So the first one is, how lightweight is the model? So is it possible to use it in production? And if so, what are the minimum requirements?
So we basically just trained like a VAT base and VAT large model. So like VAT base is like 86 million parameters with like the decoder probably like 100. So you can definitely easily run it on like a standard GPU. Okay.
And the next one is about the fine-tuning and the downstream tasks. So you probably guys have a built-in intuition about like what might work and what might not work. So do you have like tips and tricks on how to design like the model to run, for example, classification or segmentation? Like maybe like the sampling strategies that are best, that could best work for example, crop classification, or I don't know, like road detection or anything?
I wouldn't say that it's like different for TerraMind than for any other models. So I guess like you definitely need some form of like unbiased data set, or you need a lot of samples of like the class you're interested in. So I don't think there's like a particular thing you have to consider when training TerraMind. Of course, I think like the benefit of TerraMind is really that you can just use like different modalities or like combining them. So if you know, for example, like for crop classification, maybe like S1 and S2 are both quite important, so you can just use both instead of like just one. So for example, if you look for Prithvi has like another capability because it has like multi-temporal input. So for TerraMind, you would have to create like a wrapper for processing multi-temporal data, but which is still possible. So I think like the main capability of TerraMind is really like you can input like multiple modalities. So I think for use cases which benefit from multimodality, definitely would benefit from TerraMind compared to other models. So.
Okay, so building on that, when it comes to thinking in modalities, does the model have preference? I mean, like, do you need like prior knowledge to choose which modality to add? For example, like In crop classification, okay, it makes sense to add like the land use land cover. But for example, for flood detection, which one would be best, like the Sentinel-1 data or the land use land cover?
So like I would by default always just use LULC because like, it's probably like the most helpful modality because like also for flooding, like the model basically thinks about water. Or like basically it's water prediction, right? And like water as a class in LULC, so it's definitely helping. That's what we're also seeing. Like right, the MIU goes up by like 3 to 4% just by using this additional modality. So I think like every use case again, which like is related to one of the LULC classes, probably benefits from them. For agriculture, you could also think about like NDVI. So we saw, for example, that like NDVI is just one channel. So like the token information or like the information the token represents. It's like much more detailed compared to, for example, the S2 tokens. So I think like if something is related to like agriculture or something, or like predicting fine-grained structures, NVI could be helpful, or S1 of course also quite helpful for some use cases. Yeah.
Okay. Last question is about like cloudy images or cloudy patches. So for example, in crop type classification, it's very important to include like all the data set, like as much as you can. So let's say if you have like a patch and like cloudy parts of it, is it possible to use that as well, or do you need to like discard it?
I mean, the best case would be to just input like S1 and S2.
Okay.
And then the model, like if it's in your training data, the model can just learn to ignore cloud data, right? So then it can basically focus on S1 data. You can also train a model which like processes S1 plus S2 or like either of it. So like handling like missing modalities. If you have that in your training data, you can actually, like, it's already implemented in TerraTorch. You can just say, okay, like train with like 20% missing modalities or something, and then you can just run your model with like only S1 or S2 in production. Yeah, so just it's important to note, like if you want to input like S2 and you generate S1 with like thinking modalities, like of course the model can't come up with like what's behind the clouds, like it doesn't have like a limited information, right? So like that's just to consider, like we don't actually generate S1 data. It's just like we teach the model, okay, like first think about how does this actually would look in SAR data, and then it might perform better, but like just can't generate new data, just to be completely transparent.
Okay, thank you.
We have time maybe for one short question. Yeah, in the back one.
There's also like the hands-on session in the afternoon, so if you have more questions, and I'm also around, so then you can ask more questions.
I saw you had image captions as part of the training data, and I was wondering if you could comment on what's the use of text with the model, or what the capabilities are related to that.
Yeah, so with the image captions, they're actually not included in the models we open source. That's active development. So we have like an internal data set, which we're also going to open source next month. It's based on the SSL4AO data set, which we captioned with like automatic generations. You can check out the MS Clip paper for details. So we did some ablation studies with that. We have an internal model where we're exploring that, and we gonna work on that in the future. But just to be transparent, so the open source model don't support caption set.
Okay, thank you.
Okay, thanks a lot. I think it's time to close this talk. Thanks again. So now we'll be talking about LLM and AI assistants for us. So there will be two talks. The first one by Kuma about Indus, and the second one by Marcello from PySchool. And the talk is AI assistant for us, how Indus and Eve extend EO capabilities. So over to you, guys.
Good morning, everyone. My name is Kumar. I am a computer scientist working for NASA Impact. My focus currently is on building and domain adapting large language models for earth science and general science applications, and also the safety and AI guardrails, especially in consideration for science applications and downstream. So just an overview, we all know ChatGPT and the class of model it is, we all know it's a decoder-only model. But I also want to highlight that there are two other classes, which is encoder-decoder and encoder-only. Specifically encoder-only because we ended up building encoder-only model as well. The main difference between the three classes of models is in the pre-training strategy and the kind of the architectural variations as well. I don't want to get too deep into that because we only have limited time here. But essentially, in the decoder-only models, the pre-training strategy here is on the next token prediction. So input in the input space, we are trying to predict the next token given the previous set of tokens. And in the encoder-only space, there are multiple strategies, but the most prevalent strategy is masked language modeling. Similar to the EO space, we hide 15 or 20% or some set number of tokens randomly in a sentence and try and predict the missing tokens in the encoder only. And another point that I want to mention is that there are specific kind of class of problems that the decoder models are good in doing versus the encoder models are better equipped because of the efficiency. Oops. Sorry. All right, we're back. The encoder models are better equipped in certain other aspects because of the speed and efficiency and their smaller footprint compared to the decoder-only models. Just some highlight for the encoder-only models is extractive question answering. They can put a marker on a sentence on which part of the sentence or which part of the paragraph the answer is given a question. They can do really fast text classification, magnitudes of orders of compute faster than your generic decoder models. Semantic equivalence, name entity extraction, all of these are classes of problems that the encoder models can we generally call it machine understanding, NLU problems that encoder models can efficiently and effectively do better or faster even than autoregressive models. And we all know decoder models, I don't have to explain really there. A little bit more about fine-tuning in the encoder model space. It also applies to decoder models, but I will just stick to the encoder models here. The phase one, which is the pre-text or pre-training task here, which is we start with the language modeling task. In our case, it's the MLM, masked language modeling task, where we take a corpus, a domain-specific corpus specifically here. We mask out certain sentences in the corpus, and we try and produce or try and predict the masked sentences, and we do that in scale so that the underlying model here understands the underlying corpus pretty well. And this model, we take the base encoder, we change the head, we call the last layer, or we add a few last layers. Change similar to the EO models that we've seen before. We change certain, we add a few other tokens, few special characters here, change the downstream head, and change the task here, and do a downstream adaptation, give it a few fine-tuning data similar to EO models, and adapt it to a certain task, and that's how that fine-tuning pipeline is. Very similar to your EO models here. So specifically on an architectural level, let's in the pre-training stage, we have, say, a couple of sentences, and we tokenize it. Tokenization is the process of converting your text into chunks of tokens, not exactly words, but these are subwords, which there are multiple strategies of it. And these subwords are then, parts of these subwords are masked, And our pretext or MLM strategy tries to predict this mask, just like I said. And after this model is sufficiently learned, we take this and the final MLM task is changed to Squad. Squad is a data set that does extractive question answering. So specifically what's changed in the downstream head here is the start and end span. So we give the way the task is conditioned is that we give a passage, we give the start and the end span of the answer, and we also give a question for the passage as well. So the question, there is a passage, we give it a token, the start token and the end token of the passage as numeric values. And the model is responsible for predicting these numeric values given the question and the passage as the input. So we train this model sufficiently enough, and the model will predict the start and the end span values. And we take this head and in real time, we just get these numeric values and provide it a passage and a question, and it should be able to extract the answer out of the given question and answer. And that's why we call it extract to answer. There are multiple other tasks, generic tasks, named entity extraction. There are multiple other tasks as well. And this is how fine-tuning is done within the encoder space. A little bit more about the base encoder here. We wanted to have, within NASA Sciences, we have a focus of the 5 divisions. In this case, the earth science, biophysical sciences, astrophysics, and then heliophysics, and planetary sciences. So we collected, we coordinated with the science experts. We collected publicly available as well as publisher contracts, and we collected as many text as we can within the domain. And you can see the token splits here. We collected about 62 billion tokens. And we used this as the pretext for our initial index. This is outdated by a year and a half or so. We since then added more text and more domain-specific text, and we are still training, further fine-tuning the model, but we are still waiting for a concrete result. But this is a snapshot from a year and a half or so. Again, we are also exploring other possibilities like modern BERT, expanding the parameter size and all, but for this base model that I'm presenting and the link here, it was a Roberta-based model with a custom tokenizer with a 125 million parameter size MLM strategy. And we have a few application areas listed there with the resources consumed there. We also have knowledge distillation. If you're interested in testing out this model on a smaller footprint, if you're interested, and you can find that in the link as well. So I wanted to spend some time on the downstream models here. The first and the most important, in my opinion, is the sentence transformer. The way this is designed is that we take the base model, it's the same, but 2 of them, or the forward pass is done for 2 different sentences here. And at the end of the forward pass, we pull this, just collect all of the end numerical values, add them together, and find the cosine similarity between them. The idea is we create a data set where we collect similar sentences as a data set, and dissimilar sentences being further apart. So your contrastive learning strategy. And the idea is to have similar sentences grouped together. You can think of abstract and titles being ranked together, and abstract and titles of different papers being ranked or have a cosine similarity score of different, 0 and 1 being the scores between them. So this would be a example data set for this kind of a fine-tuning data set, and we train it on scale, and the resultant would be a sentence transformer. one application area is to just use it for retrieval. You can think of like a search engine where you can use this to encode your passages or documents within it, and you can use for a query or a document that you want to get similar documents for, you can use this, and there are frameworks that you can use to get similar documents out of it as well. And the Eve team is going to cover this in detail in their slides and the hands-on as well, so look out for that. And obviously, since we started with a domain-specific encoder, you can see that the last one is the Indus model, and you can see the domain adaptation score indicated by the retrieval benchmark here as well. Similarly, there is a re-ranker as well. It's a little different in the sense that the task here is we give a query and the passage as pair, and the task is the model gives a relevancy score at the end as the output, and we can design a data set for this as well. So at the retrieval we can think of this model re-ranking all the passages that are retrieved based on the relevancy score, and that can improve the relevancy and the quality of the results retrieved as well. So you can think of how this will be useful in cleaning up the results after the retrieval. And again, same case here. There is a little bit of an improvement, not much, I would say, but still some improvement in the relevancy score of the retrieval here as well. We've specifically integrated this in an operational setting where we integrated this in a retrieval environment called Science Discovery Engine, which is currently under utilization. And you can see this is like a demo. It's like a snapshot of how it is being used. And there is also an answer finder, the extractive QA, that just extracts and gets you the relevant answer for a question that is also in use, not the decoder model here in work. It's like extractive QA model. There is also some downstream applications that are made possible by the Indus model, like classifying documents. That will make easier for the scientists and domain users to find what they're looking for in the SDE. There is also some other use cases, like if you know about Common Metadata Repository, this takes a data set and assigns the keywords, GCMD hierarchy of keywords, to the data set, and it makes this easier to cluster and group the keywords together, make them easier to find for the scientists, just increasing data discoverability and quality of data stewardship. We can also see here that domain adaptation is in play here, improving across the board on multiple metrics. Conclusion, domain adaptation is the point. We have several downstream. There's a base model that you can go check out. There's also several downstream that you can also go play around. And we also have some ongoing work as well, improving the model, adding more downstream. There's also some paper based on this as well. Should we wait for the question, or should we just finish the Eve part and then?
Yeah, let's move to the Eve part, and then we go for the
sounds good.
question after.
Thank you so much.
Hello, everyone. Nice to see so many people, even if there is a strike, I think, or some delays. But we have one strike per week in Italy, so welcome. So let me start. My name is Marcello Politi, and I am a machine learning engineer at PySchool. And I'm here to present this project named Eve that we are working in collaboration with Imperative Space and the European Space Agency. So Eve is a suite consisting of domain-specific LLMs for Earth observation and Earth science, and some data sets that we're going to release open source on our Hugging Face page. What the project is about. So we are training an open source model on billions of tokens for domain adapting some backbone model. And then we're going to fine-tune it further on some downstream tasks. So mainly question answering, scientific summarization, and data extraction from raw text. Meaning, for example, that you can extract JSON from a table. Then we are also deploying the model in a RAG framework, and the purpose is to make it used for both experts in the Earth observation domain and also non-specialist users. So I put this slide for a bit of background for the Yogo community if you're not really aware of the architecture of LLMs. So I think you're familiar with the transformer architecture that was introduced in the Attention is All You Need paper in 2017. And I just want to mention that it is split in two parts, the left part and the right part, right? So the left part is called the encoder, and models like Indus, BERT are based on that, while most LLMs are based on the decoder part, so the one that is highlighted. And how it works is that you give an input a token, or a word, let's say. The model generates the next token, and in an autoregressive manner, you put back the second token in input, you generate the third one, and so on, until you reach a special token called end of sequence, and you stop the generation there. The big innovation here is the multi-head attention. So this is a layer that allows you to capture relationships among words in your sequence, and that's why LLMs have a good understanding of the text. So many state-of-the-art LLMs are based on this architecture, like Mistral or Llama. What they do is basically change something in the architecture, some activation layer, or something else. But the main innovation they do is mainly, I would say, in the data engineering part, in the data cleaning, and in the computing they provide. Because in machine learning, garbage in, garbage out, so data is really important. So now we're focusing on some experimentation on the Llama family. That is a suite of family, Llama 3, released by Meta. This is because it's open weights, and it's also easy to scale because they released the 8 billion, 70 billion, and 405 billions. So we're starting now experimenting with the 8 billion, and we're going to scale up. Just a disclaimer, we are still developing the project. So up to now, we're mainly working on the data engineering part and the fine-tuning on the question answering. Also, about Llama, I think, if I remember correctly, they trained the model on 15 trillions of data, and the context length is, so how many tokens you can put in input to the model, is 128,000, so it's good enough for our purposes. Currently, we're using Llama 3.1, the 8 billion model. The fine-tuning strategy is causal language modeling. So as Kumar introduced, it means that the objective of the model is to guess the next token, the next word. And in this way, it learns the language. Now, we're not full fine-tuning, but training with LoRa. So LoRa is a framework that allows you to train a model, but you don't train all the parameters of the model. So you freeze the parameters, but you add some adapter layers. So you train just part of the model, let's say. This is helpful because it helps for speeding up the training time, and the constraints of hardware are more are easier because you don't need such big computation to do it. And also with LoRa, you avoid a little bit the catastrophic forgetting. So what happens is when you fine-tune a model on a specific task, it might forget things on a related task. For example, I'm fine-tuning on Earth observation, and the model might forget something related to, I don't know, cars, houses, whatever topics, right? So the application areas are mainly, for now, question answering and summarization. And the cluster we are using for training is 4 GPUs of A100s of 80 GB of RAM. And we train the model for 2 epochs for 5 hours. So the data set we're using for a downstream task, this is actually both for the question answering and for the summarization. This is the distribution. So mainly the data comes from arXiv and other journals like MDPI, IEEE. Scientific papers are really good for fine-tuning on the downstream task of summarization because they're kind of labeled, right? You can take the abstract and the conclusions as the summary of the paper. So it's really good fit for this kind of task. So mainly now I want to talk about the pipeline we developed for the synthetic data generation because you cannot manually draft the data set you need to train because you need to scale up. So what we're doing is we pre-selected some documents related to earth science. And the first task is from documents that are mainly PDF to extract the text. So we benchmarked many tools that nowadays are available. And here we use Nougat from Meta, which extracts the text and provides markdown text. Then, out of this markdown, we splitted, the text into chunks. And the strategy to split the text is splitting based on section, so headings, subheadings, etc., so that each chunk contains an entire topic. It's a standalone chunk. And the second strategy is based on length. You don't want to have a chunk which is, I don't know, tens of pages. So you further split the section if it's needed. Now, among all these chunks, not all of them are really useful. Some of them only contains the author's names or the titles, or maybe something that you don't care. So we need to filter. How we're filtering? We're using a critic model that is scoring the chunk. The critic model we're using is UltraRM, developed by Ultrafeedback. It's a company that releases a lot of synthetic data sets online. And this critic model is based on Llama 2. And this Llama 2 model was trained on feedbacks from ChatGPT. So they trained Llama 2 to mimic the behavior of ChatGPT. So we're not using ChatGPT because Llama 2 is open source, is cheaper to use, is more light, you can deploy it and everything. So we have this critic model that scores the chunks. And we're keeping only the chunks that exceed some sort of threshold. Here is 0.5. At this point, for each document, we are taking 5 chunks. This is only 2, but we are taking 5 chunks. And we did some processing for each of those. So let's take the first chunk, which is about some particular topic. I want to enrich the context of that particular chunk. So what we're doing, we are taking other chunks of similar topics from our original full database. Okay, so for each chunk, I enrich the context with other chunks coming from the database. So now I have the context made up 3 chunks. Okay, that's my context. Now I query a bigger model. We're using Llama 3 70 billion to say, hey, based on this context, can you generate to me a question and an answer that then I'm going to use for my training? And this is how we're generating synthetic data. Now, the question and the answer generated from Llama based on this context, does it really make sense? So we're querying ChatGPT again to say, see if you really find this answer from out of the context. So if this sample makes sense. And based on the score of the last ChatGPT response, we drop the sample or we keep it. And in this way, we were able to generate our synthetic data set for the question answering. So to a recap here of all the data that we have right now for the fine-tuning. So we have a collection of general domain data, and this is to avoid the catastrophic forgetting. We're using the alpaca kind of data set, which consists in instruction, input, and output. And we collected 52 instructions generated by TextDaVinci 03 from OpenAI. And that's for the general domain. And for Earth observation, as I just mentioned, we have some question answering without context here. So it's like a simpler version of what I just explained. And it's 5K samples of question answering, summarization data sets that we've gotten from the paper using the abstract as the summary, 10K samples here, and the multi-context question answering that I just mentioned, and we have 50K examples. Now, we focused mainly on the multi-context because the model will be deployed in the RAG framework. So the assumption is that it always will have access to some context. So it needs to learn how to reply to some question given the context. So that's why we mainly focused on the multi-context question answering. Yeah, this is the RAG deployment that you will see also tomorrow and play with it in the afternoon in the hands-on session. So how does it work? You have the data sources that you have selected, and you need to clean the data, extract with NuGet or whatever, chunk them, and embed the text in your vector space, in your vector database. Now, you can use, most providers have embedding models like OpenAI, Mistral. What we're using, Indus, obviously, because it was fine-tuned on similar topics. And we populated in this way our vector DB. So what happens is when the user query the model, also the query is embedded, and we retrieve the most similar documents in the database. Then we enrich the user query with our prompt template by putting also the context, and this is the final prompt. So now we can query Eve, the generation model, saying, hey, based on the user query and this context, can you provide me the answer? And that's the answer. We're also working on a fact checker method that is not, it's still under development, so we're going to release in the next upcoming months. So this is the RAG framework. We already have a working demo that we will show to you this afternoon. Okay, regarding evaluation, still working on this, so it's really a tiny initial work now. We collected 360 samples of open-ended question answers from Earth observation courseware. And among these, we selected the 50 hardest samples that we're using for the evaluation of our model. And what are the metrics? We saw that common metrics in NLP like Rouge and BERT score are not really sufficient to evaluate our model, because Rouge, for example, is based on n-grams. So if the model answer and the reference use the same words, but the semantic of the syntax is different, the score is high, but it's not what we want to. Or for example, in BERT score, if you have a sentence and the hypothesis and the reference, which are the same, but you put a not in front of the sentence and the semantic changes completely, the BERT score says that those are really similar and the score is high, so it's not really suited. So what we're doing, we're using LLM as a judge. So given the hypothesis and the reference, we ask to SOTA models like ChatGPT, Claude, what do you prefer? And we have a winning rate. I didn't put the results here because we just got the results yesterday. So we have, from LLM as a judge, a winning rate of 60%. And also we have some annotators that are putting their preferences against of Eve against the Llama instruct base model. And we have a winning rate of 80% over there. So it looks like people are preferring the answers given from Eve rather than the Llama basic model. Yeah, so we're going to have a hands-on session, and we're going to release everything open source on Hugging Face. What I would like to see in the future, I saw that many people are working on agentic systems here, and the core models in their system are open source models like Llama. But I would say that Eve would be more suited because it will understand the user intent to use all the tools that you put in your agentic framework more easily. So I would like to see this kind of application in the future as soon as we release the model. So see you this afternoon. Thank you very much.
Any question for Marcello or Kumar? I guess you are just waiting for the nice coffee served there. Okay. If no questions, so I suggest that we break for 30 minutes, and then there will be a further discussion and presentation on infrastructure after that. Thanks a lot.
Okay, so we're almost on time. Thank you for joining us today, and just giving a few more seconds for people to come in while you take your seats. This session is an invited session, and I have the pleasure to chair this session together with my colleague Luca Girardo. It's a session about infrastructures, so we're going to be looking a bit into the future, see what is happening today with the current infrastructures that are being put in place. There are a lot of evolutions on the horizon. So I think that we have a very packed session today. We're running against time, so I'm not going to spend more time on the introduction and just start with our first speaker. So I'd like to invite Gabriele Cavallaro on stage. And I will let him introduce himself, but maybe we can bring up the slides. Thank you. You have about 12 minutes or 15 minutes. Thank you.
Okay, thank you very much for the introduction. Very happy to be here, and very nice to have such a session in the workshop on foundation model. Yes, my name is Gabriele Cavallaro, and I'm with the Jülich Supercomputing Center in Germany, but I'm also a professor at the University of Iceland. And I'm here, as you see, the title is quite a long title, but my idea here would be to expose you as a community to the world of computing, supercomputing in general. So I think we would all agree that building a foundation model is multidisciplinary. We require different expertise institutions working together because they provide different set of expertise in order to arrive to the model that we define foundation. So it's very important that the communities work not in silos, but they communicate to each other and understand what are the different challenges that they face. In this room, I'm sure that we all are well aware of challenges we have in Earth observation, remote sensing, but maybe you have not touched some of the different challenges we have in computing, supercomputing. So this is my idea. So in order to do that, I will have to touch 3 points. I will start with some background and good news achievements that we have in the domain of computing. Then I will move on more on the evolution of computing technologies. It's very important that we also understand where we are coming from, the different aspects, the different evolution that computing has gone through, in order to understand also where we can head and what we can aim at in the next decade. And as I said, I'm not here to give you just slides and just show you how the system are big and the good news. I want also to expose you to the different challenges and the sustainability trends that we need to face. So background, what is a supercomputer? I will try to be quick. I know I don't have a lot of time. But the key message is that a supercomputer is basically a huge number of compute nodes. You can see compute nodes as a worker, which can talk in a very efficient way to the other workers. So you have a number of compute nodes, you will have a lot of memory, but most importantly, you have a very efficient interconnection, so network. So you will not spend too much time in talking, so in communicating, but you want to spend the majority of the time in computing. So you might wonder what is inside a compute node. A compute node, basically, as I say, is a worker, and a worker can be a different person. It can be a specialized person, it can be a general worker. In this case, what we see now at the trends is that in compute nodes you find GPUs, and GPUs are now also selected as the enabled technology for exascale supercomputing. And you see here a graph where it shows you basically what are the different vendors and some nice trends. So we are now in era of exascale supercomputing, which means basically 1 quintillion of operation, calculation per second. This is the threshold that we set up in order to define a system, exascale system. And this was already achieved actually in 2022 in the US by Frontier. And this will happen in Europe soon. It will happen in July, August, in summer at the Jülich Supercomputing Center. We will have the first exascale supercomputer in Europe, which exactly will achieve this performance. This is just a nice visualization. What it means, if you want to visualize it in your head, would be basically putting 1 million of smartphones all stuck together that will reach the peak of the Mount Everest. This is just, of course, visualization. So what we have, Jupiter will be a modular supercomputer, so it means that you will have different modules. Here I will focus more on the module, on the booster module, which will include 6,000 nodes, compute nodes, the one that I was referring before, and inside each node you will have the following hardware. So you will have 4 NVIDIA Grace Hopper GPUs with very 96 GPU memory. You will have the interlinking together with CPU Grace and very well interconnected with Mellanox InfiniBand. So here I also give you a QR code, so everything is available online, so I don't want to spend too much time again in showing you the different features of the system, but you can expect that in summer this will be operating, and the next opportunity for you also to apply for computing time will come next time in August, September. So I will also tell more about also opportunities to access these systems. So what are supercomputers used for? Well, the supercomputers has been there for a long time. Also, let's say before AI became, let's say, one of the main field that now people see HPC with. So you can use it for different discipline applications, very different one. I was just to give you an example here that was featured in November at the supercomputing conference. Is basically a very nice application that you want to detect flash droughts. And what you could achieve this, people at Argonne National Laboratory, what they did is to use 10 years of simulation data and also coming from different climate models. And this shows you how very important it is to preserve this data, because then you can use them if you have a system and that can run this simulation. In this case, they use 1 million node hours. And this enabled to achieve predictions that, of course, we don't want to hear, but this is just a reality check that things are getting more in the negative side, especially when it's about predicting these events will tend to increase in different parts, for example, of North America, as you can see here, especially in the California coastlines. So what we can see and recognize is that in the scientific communities there are different trends, and from the HPC side we recognize this. So we see also from the Earth observation we have more digital twins coming up. We have foundation models, obviously, that's why we have a workshop. We will have also different scenarios like data simulation, interpretation. We will have different also data sources that you will have to deal with, like streaming data, but also dealing with different sources that this community is very well aware. One important aspect that I want to really emphasize here is that the main challenge, and I think we're also aware very here, is that moving large data volumes is now the main problem. And so from this perspective of observation, we have data generated by satellites, okay, but in computing, in exascale computing, we have also data generated by simulation. So the key message is that actually compute is much easier to move than data. So here I just want to give an example of what I mean. So it's just, it's not observation, it's just a very, let's say, detailed simulation about thermal convection that allow you to also to do a very nice study about how things interact with the different, for example, atmosphere and planetary interiors. But the point here is that this simulation was run on 3,300 GPUs. So, and in order to achieve the level of details, probably here you cannot really realize the quality of the way how these interactions are produced as a 4K video. This could only be, let's say, visualize only at the compute node side. And here I want to make the point. So if we now take the feature that we have, that we'll have at the Jupyter system that will coming soon, as I mentioned before, if we look at the peak performance that we can expect, so what is the amount of data that can be generated theoretically using the whole system? We're talking about 3,500 petabytes data a second. And you can see that if you now want to move away from where the data is generated, obviously you will start to lose the data, because then you have the different memory bounds that you will have at the node memory, where you start to lose data, and then you also will start to lose it when you move more on other different compute nodes. So the point here is that at the end, if you really want to achieve and you want to extract the best of the best information that you can achieve from simulation using as a scale system, this would be a one point to really consider. So as I said, in HPC, we can say that the high fraction of the hardware goes into the network because we don't want to spend too much time in communicating. We want to spend time in computing. And here, I think, is a very nice set of points that I'm actually taking from a very nice talk I was witnessing a few weeks ago, where basically we take the 8 fallacies of distributed computing. This is basically points where, whenever you want to make a program or computing for a distributed system, you assume that, for example, the network is reliable, you don't have latency, low latency, and etc. So these are all points that HPC, when an HPC system is built, people will really try very hard to make sure that everything is really fulfilled. However, as I mentioned before, the problem is data. The transport of cost is not negligible. This is something that even by putting a lot of effort, money, and hardware, this is something that you need to take care of. Okay, too much for this. We need to go now to some news. I will go very fast here because these are all public information, but I just want to make sure that we are all aware that we have funding, we have a lot of news coming up from the Europe side. So here I just want to show you that access to HPC is free. You can all do it. You need to write a proposal which will be evaluated, and then you will be able to access the system on the different side that the Euro HPC joint undertaking is providing. Here I just named the top supercomputers that are available right now that were ranking at the Supercomputing Conference in 2024, Lumi, Leonardo, Mare Nostrum 5. You see very good web running in the global. And this you can access this system. We will have different mechanisms, national part and the HPC side, but if you just Google them and you will find the all information. AI Continental Plan, I'm sure you're all aware that this came out, and I want to here just emphasize that you will have they have identified different components, skill data, simplified rules, but I would like to focus more on the computing infrastructure. In the computing infrastructure, if you look into the plan, you will find these following components. You will have the AI factories. This is something that I want to talk to you later, which most focus on the train and fine-tune of models, so inferencing, using it for connecting Quisto to industry, SMEs. AI Gigafactory, this is another plan that is now current and under discussion, and we will see how things will go in this direction, and also more work in the cloud part, which is also very important, and I will also talk more about this later. So HPC AI Factory, again, everything is available online, but the sites has been identified in a preference where there is already a system that is very well prepared for training, heavy computing, and then you will have an AI factory which will help you more to, let's say, do the moving from the model, the training, and to the deployment and the usage for the different community startups. In Jülich, we will have also an AI factory. This is something that is under development. And what I want to basically show here is that it goes integrated into the Jupyter. So Jupyter is a modular system, as I mentioned before. I showed you before the booster partition. We will have also a cluster system partition, but also the AI factory, which will have this very nice Jarvis, we call it, Jupyter Advanced Research Vehicle for Inference Service, which is basically hardware well dedicated for inference. Okay, I wanted to continue on that, but I'm sure we have not much time. What, 2 minutes? Okay. So in order for the sake of time, I just move on very quickly in this case. But I just wanted to show you that if we look at the trend, the exascale actually took more time to get to the point of exascale computing rather than we once expected, because there have been different type of evolution in the computing. In a nutshell, what happened is that before 2005, basically most of the computation was provided by the fact that the hardware was getting better from the semiconductor technology, more slow. But after that, actually, the improvement came from actually the top. So from improving the different architecture, the different programming, different tricks, different way of dealing with the software. Starting from providing parallel computing with multi-core era, and now moving more on the hardware. So to sustain these trends now, we will see that, I showed you before inside the compute nodes, we have GPUs, but actually the trend is to go even more specialized. So you will find that eventually we will have more dedicated hardware that will be prepared for taking different applications. So computing architecture are becoming increasingly heterogeneous. Here are just a few examples that will appear more often. And basically, this shows you the trend that you start from some specializations, then you move to a generalism, like ChatGPT, but then you move on again to hyper specialization on a specific task. And this also is happening with the computing. And this is just an example how this was done, for example, by introducing Tensor Core. So that was the same GPU technology, but then you use the Tensor Core specialization, and you will achieve already more performance. So that means that it's just a headache for people who will have to program and dealing with different workloads, because it's not just about offloading a computation to a GPU, but it's now about dealing with computation coming and be done on different hardware in a concurrent way. So it's even more complicated. So basically what we can say is that compute is much easier, as I said, to move the data, and then heterogeneity will grow. So at the end, we will need to have, looking at the future, we will have to have a different way to deal with this. For example, looking at orchestration, make sure that you will have different workflow that can run on different systems in a proper way, in a more efficient way. There is a vision talking, which is related to computing continuum, where you have different components, different data coming from different sensors, and HPC will be just one part of it, where you will be able to deal with the data. But that, of course, will require different changes in the way also our HPC systems are operated. One solution, of course, federation. Here I'm stealing a slide from the kickoff, or from one of the presentations was done this year about the HPC federation platform. So there is their strategy project in order to make sure that the HPC system that will be developed are well interconnected together more efficiently. We have also this power part where basically in the last decades, HPC cloud has been very well defined and divided, but actually this wall might get less present because of the technology. Networking is improving, but also the way how you do computing on the infrastructure might reduce latency, meaning that some workloads that before were running on HPC now could run also on the cloud. Okay, I think the time is almost done, but so the trend is clear. We're building bigger system, bigger models, so this is sustainability as under discussion, and of course also systems that are now run by companies are the one that achieve the higher performance, the more spending and the higher performance. It's crazy to see how we started from AlexNet and we moved to GPT, the change of time and the change of spending amount and the models. So this is a trend. I will move on, but basically because of course you can find many different data online, but the trend is clear. And of course to that there are different solutions that you can use in order to mitigate this approach. For example, decentralized training or lower precision arithmetic. So we need to work on this solution in order to make sure that everything could work. Of course, there is also this little detail of technology dependency, which as well touch quickly. As you know, semiconductors are coming from specific places in there. So given the current scenario, is something that we also need to consider. In fact, in Europe, there will be a new follow-up project that starts. So in 2018, we have the European Processor Initiative. And this project here, there is just a major follow-up on that to make sure that we can also follow on this direction. So with this, I conclude. Thank you very much for your time. I think the slides will be available. So eventually, you will find some different, let's say, points and reflection that you can also have a look and maybe want to discuss with me. But for the meantime, I will just stop here and thank you very much for your attention.
Thank you very much, Gabriele. Maybe we have one question from the room.
Thanks a lot. That was a really great summary. I wanted to ask you about this aspect of specialization in the hardware, because it seems for me that the industry is very well aware of that and adapts very quickly because they are afraid of being outcompeted. But at the same time, we also know that the governmental side is investing heavily into infrastructure with the HPCs that you have shown. Do you think that they are aware that it's not only enough to invest in these big HPC clusters, but they need to be very agile and they need to be specialized and adapted continuously.
Yeah, this is exactly why I wanted to show you this aspect. So it is well known, if you go to conferences like Supercomputing Conference or the EuroHPC Summit, this is a very ongoing discussion to make sure that at the end this barrier that the user have to access this system is as smaller as possible. In Europe, the strategy is to explore as many technologies as possible. So if you look at the supercomputers, you will find different technology, not one just specific GPU. Of course, the majority, we know which vendor is, but there are also other technologies that are put in place. Just looking at quantum computers, for example, quantum computers, they just bought, they will install completely different technology to each other because we want to explore this part. In terms of accessibility, there is still work to do. Of course, the point is that we should not put burden on you to try to figure it out what is, how to, make sure that, you get the best performance. All these projects that I show you are in place to make sure that, at the end, when you have a problem in application, the workflows will set up for you the best way of tackling the different processing steps on different partitions and maybe hopefully across different systems if you have, of course, computing time that you have secured there. So yeah, these are all challenges that are valued and hopefully, if we don't work much more in silos, but also we communicate more the different challenges between us, this can only improve.
Thank you. Thank you. Let's thank again our speaker and we'll proceed with the next. Okay, so I would like to welcome to the stage Peter Gabas, talking about the space HPC.
Hello, good morning or good afternoon, everyone. That was a fantastic introduction to the HPC topic. Thank you very much. So I can basically just jump right into it. So I will very briefly introduce the space HPC. My name is Peter Gabas. I'm an AI engineer at ESA, working in the IT department. So what is the space HPC? So the space HPC is the first HPC system that we have built at ESA. Let's say it's brand new, so freshly inaugurated. It's actually located right here in ESRIN, behind the building. So maybe you can see it like from a distance. This is a new system, and it's fully dedicated to the European space industry. We built it as a modular system, so it's, let's say, a couple of containers that are hosted with some infrastructure. And it was nice already that was mentioned all the use cases for the HPC, so I think I don't have to repeat it, but for us at ESA, we also need to run complex simulations, train machine learning models, and so on. So, I mean, the use cases are really vast. With this system, it's quite a small system. We aim to be sort of like an incubator, both for ESA and outside ESA, for small and medium-sized companies. Basically, they can use the system to learn a bit how to work with such clusters and then possibly move to the bigger ones. So very quickly about the benefits. So as I mentioned, we would like to accelerate the innovation in the European space industry. For industry, we're going to focus on the smaller companies, and it's also the computing cost is for free, at least until end of this year, or we are pending, let's say, budget and discussions, but yeah, this is to be evolved. And we would like to de-risk the activities that some companies have. For the ESA workforce, it's also very easy to apply and use the resources. It's first come, first served basis, of course, with some limitations on the maximum amount of compute one can use, because, as I mentioned, it's a relatively speaking smaller system. We will also have some free trainings from experienced trainers, so this is also something that could be interesting for people who not yet developed anything on an HPC system, to learn how to parallelize their applications, how to work with these systems, so this could be also interesting. Yes, and also we are pending PL2 certification, so it's also good to work on more sensitive projects. And with the technology, when we were designing it, we went around ESA, all the directorates, and we asked for their input. What do people need? For what kind of use they need to, for what use they would like to have the system. And as mentioned, it's like the trend is it's more and more specialized, right? So we opted out for quite a flexible architecture with available budget that we had. So we have like a CPU partitions, we have some GPU partitions, and some dedicated specialized nodes. I will get to that in the next slides. And the network, also as mentioned, now you have a bit of introduction, is very important. So we had to spend also a lot of the budget proportion went to the high-speed networks that are interconnecting all these components. So how does it fit into the wider ecosystem of HPCs? As mentioned, this is, for us, this is the first HPC, so we want to build the in-house knowledge at ESA, how to operate and these kind of systems. We also want to use it to accelerate the development for the smaller companies and to basically learn. And if the projects are requiring more resources or are more mature, we encourage them to use the existing national HPC and the Euro HPC networks. So a little bit about the infrastructure. I'm not sure if you, I think it's visible. Just a little bit to spend on that. So as mentioned in the top, we have like a general and fat partition. Those are used for the classic CPU workloads. We have about 34,000 cores of AMD EPYC Genoa. For the GPUs, we have accelerated partition. That's like 4 GPUs per node. And then an AI ML partition, which is 8 GPUs per node. Together, we have 108 NVIDIA 8100s. We have 2 InfiniBand networks, the high-speed networks. One is for compute and one is for storage communication. The system, as shown on the picture, and maybe you can also see it later on, it's using a combination of direct liquid cooling and air cooling. It was briefly mentioned also the sustainability aspect, so we try to take that into account as much as possible. So we have quite a good power usage effectiveness of below 1.09, which means that most of the power that goes to the system is used for computing and not for cooling. As you can imagine, it's very dense in the container, like the GPUs are hosted quite densely, so like the cooling is very needed, and yeah, that's one of the big topics you have to solve. And lastly, some experiences that we had so far and a brief timeline. So currently we are in the test and commissioning phase of the project. So we are running a lot of benchmarks, and we are trying to figure out the best environment for the users. So we plan to, let's say, launch more outwards to everyone in June. So far, we also, when the system was being assembled, we had remote access to the factory, so it was nice that we gained some time, let's say, trying to test and set up everything. And some of our early impressions, yes, building an HP system is very complex, as we heard before. We sort of learned that the hard way, of course. There are like hardware issues that you have to replace, because these things are also very much prone to errors, especially the GPUs. Also the cooling, you have to test for leakage and these kind of things. So it's very complex, but we are getting there. And you can see also our benchmark results. So this might be still improved because we are fine-tuning the system, but for those of you interested, just like there are some numbers here. And lastly, so for contact and questions, we have a website on the commercialization side of ESA, so you can see the link there. There is some more information there, and there is also an interest form that you can fill in. It's just like, I think, 6 fields or something. It's very easy to fill in. You can sign up here, and we will contact you once the system is fully operational. One thing I didn't mention, I had it on the slides, maybe I went a bit too quick. As I mentioned, we aim for the industry and for the companies. Currently, the process works that it's aimed for companies who have some kind of contract with ESA and or partnership. So this is in this phase. For internal researchers at ESA, there are no requirements. This is for also the security reasons and that we have. We also have a series of webinars, so the next one is in 2 weeks, on 20th of May. You can sign up on the learninghub.esa.int. There will be a bit more, we will have a bit more time to go into detail how the process works if you want to sign up and get resources. And finally, you can also reach us directly on the spacehpc@esa.int. If you see us around, our 2 colleagues, Neva and Sean, are somewhere in the room. you can, Neva is there, you can talk to us over coffee or something. And yeah, that's it I think, from my side. Thank you very much, and happy to answer some questions.
Thank you very much, Peter. I don't know if there are any questions from the room.
Thank you very much. I would like to ask a question. And you spoke about data security. You spoke about the fact that you are undergoing a PL2 certification. That is quite an interesting aspect. And I would like to know a bit more about the challenges for getting to this certification in place, and what would be the impact for the user? Will be that transparent, or will be?
Yeah, that's a very good question, and indeed it's very challenging to get the PL2 certification in system that's open, let's say, to the public, let's say. So we have, the system is made in a way that it's like, when it works with the PL2 data, it's completely isolated in a way. So like security-wise, it's not even like the system administrators sort of can access the data. It's like completely separately. There is no information linked about the project and the user towards like outside. So it's yeah, let's say you get a special user, special project. So it's this was quite a challenge to set up, but we went over also with the security to let's say have it in a way that's applicable. And what helps, of course, is that it's hosted on site. So also like the security in terms of like physical security, we can then guarantee that we host it on location.
Thank you.
Thank you very much. I was ready to leave.
Okay,
thanks.
Thank you, Peter. Just waiting to see if there's any other question. Okay, so our next, we saw what happens in Europe, so I'd like to invite to the stage Kevin Murphy of NASA to give us a bit of an overview of what's happening in the US.
Hello again. Yeah, so I think similarly to what we've just seen, NASA really isn't in the business of building large supercomputers. We're in the business of launching missions, doing science, and human exploration. So when we look at our architectures for how we support machine learning, we look at our architectures for how we support computational fluid dynamics, and access to our information. It's really as a way to partner with other larger organizations that may have those computational capabilities. Just to give you an idea of kind of the reach of our current information, right? We've got about 15 million users a year that come and use our information, specifically the science data, which is open. We have about 700 petabytes that we expect to have available in the future. We support about 160 different missions and instruments right now across 5 different science domains. And once we launch NISAR a little later this year, we'll be ingesting around 50 petabytes of data per year. So the actual infrastructure to do this is incredibly important, both in terms of how we extract scientific information from the information that we collect, but also how we make that publicly available to everyone. So over the past couple of years, we've embarked on an effort to try to consolidate a lot of the types of systems data and capabilities that we have. We've conducted a data and architecture study. We've just concluded some high-end computing Tiger team activities. And we've, basically created a reference architecture where we are going to be consolidating a lot of our existing capabilities. As you imagine, NASA's about 67 years old now, and we have a lot of really dedicated IT systems, which we're trying to put together in a much more kind of coherent way to support our work in the future. So. We conducted this activity, and what we did is you know, we really worked with the communities. We really looked at how we support open science, how we support the public access to this information, and where we see the user communities going in the future. So we have a pretty technical audience here, but when we talk about everyone that could potentially use, especially our earth science information, our lunar data, our heliophysics or sun information, Mars, astrophysics data, it's a pretty wide group of people, right? And we need to make that information accessible, open, and fast enough for them to use. So the first step in that is discovery. So how do you find not only the publications, but also those products that you may want to be developing your foundation models on or other AI techniques? So we have a thing called SciEx. I don't know if anybody here is familiar with the astrophysics data system, but that's a capability that indexes kind of like archive, but it preceded archive by quite a bit. A lot of the scientific articles that we have across our 5 science divisions. And we use that when you heard about the INDIS model earlier to train those types of models, okay? So that's a publication database full of a lot of really rich information that we can use to do a lot of training. We have this thing called the Science Discovery Engine, which actually indexes across our about 70 or so archives across the United States, exposes about 95% of all the software and data that we've got. And then we have a portal where people can go and use that information. So as people try to interact with our systems, the question about how we find that information, I think, is incredibly important, and how we do that in ways that make things usable. A lot of these things, I guess when I presented on Monday morning, we talked about accelerated discovery. So what you'll probably see in the next year or two is these being consolidated into one accelerated discovery service with a bit more easy interaction across these separate systems. We have basically a plan for how we're doing all of our services. This is a basic reference architecture system, or diagram, and you'll see a lot of consolidation in each of these areas over the next few years. Hopefully you won't see it, you'll just be able to use it. We have, of course, our IT support services, our cloud and HEC services. Most of our data today is on public cloud infrastructure because we want to have people be able to access that information without having to move it pretty quick, move it too much. We've done a number of studies where we see, trying to move full mission archives from one group to the next. And historically, that's taken quite a long time if we haven't been able to process it directly in the cloud. So for instance, we have a Terra mission that's been launched since 1999, and it's got probably one of the most relevant records for earth science and impactful records with like the MODIS instrument, Aster, so on and so forth. It's getting pretty old now, but we had a study that tried to combine all that information at one point, and it took about 9 months for the PI to actually gain all that information, move it from the separate archives, and put the level 1 data in one spot for people to process. So having the information in one spot is incredibly important. Addressing the cost issues with commercial cloud versus on-premise is a significant issue, frankly, in terms of what those processing costs are. But if you look at the staffing costs versus the processing costs, we see it pretty reasonable. We do have, high-end computing infrastructure at our Ames facility. We have 5 compute clusters out there that provide, basically a stepping stone to get to the DOE, or the Department of Energy Systems, so that we don't have to invest in those pieces of infrastructure. We also partner with other folks across the United States and especially in Europe to run some of our larger models, especially where we see an intersection between organizations, right? We would prefer to invest our funds in launching missions, study, basic science, and then really partner with organizations that have these capabilities to do this work. Our Solar Dynamics Observatory foundation model that we're creating is going to be run on the NVIDIA supercomputing clusters, and we really see that those kind of activities are very beneficial to us. So I think my kind of closing remark is that computational systems are really important, regardless of whether they're on-premise or in the cloud. But it's really all the services that go into making that usable to a wide group of people, which are some of the most expensive and impactful things. So as you look at making these available, I think that that's an important component. Thanks.
Thank you very much, Kevin. Do you have any questions from the audience? So you spoke a little bit about partnerships and the importance of that, and I was wondering if you have already some, let's say, collaborations with Europe that are worth mentioning now, or how do you see this also based on the presentations that were
so we certainly worked with ULIC supercomputing, which was incredibly important for the Prithvi HLS-2. And we really are going to be looking forward to additional partnerships in those areas in the future. So I think these are open data sets, these are open science problems that we have, and we really like the ability to share that with more people, and we'll continue to kind of focus on those efforts in the future. Thanks.
Thank you. Thank you very much. Let's move on then. To our next presentation. The next speaker is online. Just checking with the technical colleagues if we can bring our next speaker on the screen. Yeah.
Hello.
Great, thank you. So it's my pleasure to introduce Maciej Grzanowski from Cloudflare. I hope that you can share your slides.
I will try in a moment. Of course, I wish I was with you on site. Everything would be easier, but I hope that anyhow I will be able to share the point of view from the industry perspective, European industry, and I will try now to share my presentation. Do you see this? Have I succeeded?
Yes, but we're seeing the presenter mode, so I think if you can just switch to the...
How can I do this? So you see my first screen, yeah?
Yes, we see the presenter view. I think it's one of the buttons on top. To the...
Yeah, let me check this.
Below the slides, they say. Below the slide view, there is...
Do you see it now?
Excellent, yes, it works, perfect.
Technology, beautiful.
You
okay.
switched to the other one, sorry.
Is it okay now or not?
No, you brought back the presenter view, so if you can do what you did before, it would be great.
And now?
Yes, this is good.
Okay. So again, hello everybody. I'd like to present what we see from the point of the industry, also commenting on previous presentations, because some subjects are exactly repetition what, for example, Gabriele said. And I would like to advocate for a kind of integration or synergy between HPC world and cloud integration. So what we see, let's check. How it looks in Europe. It's in a sense we are operating in two worlds that are cooperating one with another, and one is connected to institutions, academia, and research world, and there are very big investments into HPC infrastructures, and like the ones mentioned before, also at ESRIN. So we have Euro HPC, HPCs and AI factories and planned AI gigafactories. There is a new space HPC in ESA. And there are also places where there is a lot of data. Yeah? Europe has a lot of data, and this is an obvious advantage of Europe. One running example is Copernicus data space ecosystem. So the place where all Copernicus data is available, is cataloged, can be processed and used. On the other hand, there is business. And here I would like to talk about the business that is in line with the idea of sovereignty. So based on local technical capacities, based on local competencies, and independence from some intellectual property rights that could be. So basically, this is the business, the computing business based on open source. So in this business, the normal modus operandi is the cloud computing model. So infrastructure as a service with computing, with storage, with all necessary services around this, with platform services, software services. Then there are also data holdings as a service. For example, technical realization of Copernicus data space ecosystem is realized as a service by cloud computing providers in Europe. And also, we are here discussing AI, so there is a growing part of AI tooling from just pure infrastructure as a service, like GPUs as a service, through some managed services like the access to large language model for foundation models. So we have two approaches and two sources of investment into the computing and data access. Now I would like to comment why what we can see in some features of both approaches. So in case of HPC, it was mentioned before that it's an architecture meant for heavy jobs, like model training, like models, like physical simulations. So a handful of very big jobs and rather a smaller number of users, and rather a very well established governance for big number of users. Yeah. So if you compare it to this was mentioned before that one can see a problem with getting data or to the data from HPC. So it's easier to move. I think Gabriele Cavallaro said this, that it's easier to move computing than the big amounts of data. So obviously, if this is going to work, data somehow has to be made closer to this computing. But there is also an issue of users. Users have some, they are accustomed to some ways of doing things. And if you look at cloud computing, the governance of multi-tenancy, privacy, billing connected with budgeting, and quick provisioning, this is a normal feature of any current cloud solution. So it seems that while HPC are featured for big computing tasks, the stuff connected to, let's say, consolidation of data, automation of tasks, repetitive tasks to get the data and make it ready for use, and also tooling, prototyping, things like this can be done on the cloud. And also to cheap data storage, because you have to have data close to HPC, and you have to have results of modeling done by HPC stored somewhere, and obviously probably not on HPC. And also because of segmentation, everybody wants his results, for him. There is also an issue of connectivity, and again, cloud is based on connectivity and security connected to this connectivity. So at the end, I would say that there are fitting features from both sides, and there is a natural fit from between HPC and cloud solutions. So I would say that this kind of cloud bridges or extensions to HPC would be a natural place for European cloud industry. That's why this is a place. I would like to present it on an example of our company. There is a little bit of marketing around this, but at the end of the day, what's important? What we see here is that that on one hand we are a technologically sovereign company with open source solutions and with local competencies and local physical capacity to do things. And on the other hand, we are specializing in things connected to space and specifically to very big data sets. Currently, we are running an 80 petabyte archive for Copernicus data space ecosystem. So it's slightly less than NASA does, but not much. And again, this is done by the industry. What would be the solution I would like to advertise or advocate for? This fit between big HPC type infrastructures and cloud computing, private or public solutions placed close to such HPC factories, because cloud can provide user governance in a way that users are used to, additional tooling and that could be used for prototyping and anything that should not burden the big infrastructures. I mentioned big storage, and of course broadband connectivity. And of course, what's very important, and this was mentioned here, easy broadband access to data platforms. First such platform is, of course, CDSC, Copernicus Data Space Ecosystem. And this is already present in European industry, as we are a European company. Why we are here? Because, as I said, we are running the repository for Copernicus, and we are a reference data source for Copernicus, and also cloud solutions close to this repository. It's branded CREO-DS. By the way, this is also a natural place to make some preparations of data for AI, like embeddings, but I think that Mikołaj from Asterisk will tell more in the next presentation. On the other hand, we are also doing cloud bridges for a destination Earth data lake. So we have cloud installations placed at all the supercomputing sites mentioned before, like Lumi, Leonardo, Mare Nostrum, for the destination Earth data lake. So we already know how to integrate with HPC, and we provide features I mentioned before. Now, if we look at the specific tooling for AI, because AI is now an obvious subject, we can provide everything from the very bottom of services like GPU as a service. I don't say that we have the same capacity as AI factory in, for example, Jülich, but we can serve significant needs of customers. We are also working now to, we have some solutions where we just provide platform solutions to train and use models. This is under our brand name Cloudflare Sherlock. We are also working to have managed solutions like managed Kubeflow, for example, to make use of AI easier. We are and were engaged in the generation of embeddings, but I would not like to go into details. Basically, what I would like to summarize here is that we see a need and a necessity for cooperation between the high-power computing world and the world of industrial cloud capacities. And we also, I would like to say that we are already ready to provide such services basing on our current references and current experiences. So, not going into the marketing details. That's it.
Thank you.
Let me try and
Is there any question in the room?
So thank you very much for your presentation. I would like to ask you a question about a bit the business model. So the solutions that you were, let's say, showing us in terms of, let's say, integrating HPC with cloud, offering commercial services on the cloud that are, let's say, bridging towards HPC. Now, how do you see the business model? So how we make it rental and in terms of resources, also in light of the fact that you will have competition from AI factories and so on. So how you see the business model be impacted by the introduction of the AI factories that will soon come?
Basically, I believe that since there is a need for this cloud part, there is a market possibility of the need to buy probably private cloud solutions to be put close to HPC installations. And this is a market opportunity as we see it. We can easily extend such private installations by also public installations for, let's say, overflow amounts of computing. We have public installations in several places in Europe. So, answering your question, a mixture of public and private clouds. And in case of private clouds, I would assume that there is going to be a market need to install such installations close to AI factories. So we are one of the potential players that could put such installations close.
Okay, thank you very much.
Okay, let's thank again our speaker. Thanks for being with us today.
Thank you.
And I'd like to invite our last speaker from Asterisk Labs, Mikołaj Czerkowski. Mikołaj, you have the floor.
Hi, everyone. I'm very much aware of the time. We have -3 minutes to deliver this talk. I will try to do it in -4 minutes. I might fail, though, so that we're ahead of time. My name is Mikołaj Czerkowski. I'm one of the 3 co-founders of Asterisk Labs, the first research laboratory in the UK formed as a worker cooperative by 2 recent ESA-Lab research fellows, myself and Alistair Francis, and 1 amazing London tube driver turned scientist, Jacqueline Campbell. In any case, I'll cut to the chase. This will be about the vision for AI-powered archive-level insights from Copernicus data. Okay, that works. I'll start with a few questions, and just to frame what we're really after in what I'm about to present. So programs like Copernicus offer us an unparalleled resource to study our planet, but how do we make sense of these vast archives at their full scale? And when we talk about full scale, we really mean full scale of archives. So the answer is in the title of this event, Foundation Models, AI, and Large-Scale Processing. So what conditions exactly do we need for AI to grow organically in Earth observation, right? So we have quite a lot of things figured out by now. So we have a stream of data from the satellites. We have some data archives. We do have data distribution systems, and that's already in place, right? We have amazing programs like Copernicus that are serving very high numbers of users. But we could probably do better on the front, on the interface of the data distribution systems and the actual AI community that is developing AI. So I think the notion of AI-ready data is becoming more and more relevant as the AI develops and as our archives grow beyond the scale that is feasible to process with traditional methods, right? And when we have AI-ready data, there's a lot of organic action going on. So as soon as we make the data available and easy to process for a large community of users that might not be experienced in EO data, we will see a lot of models and interesting things happening on their own without our support. So the rectangular pieces is something we just have to provide as the EO community, but then hopefully we get a lot of things back just because people have an easier access. And then we can think probably of a loop, because all the things that grow organically in the community might result in tools that support our infrastructure. So we can probably think of a continuous stream of developments and AI community that supports the EO community and vice versa. So when we talk about AI-ready data, what do we mean exactly? I mean, we probably should start thinking about some definitions for what we mean exactly about AI-ready, but there's definitely things that when we see them, they're definitely AI-ready. So one example of that is a project that has been mentioned here many times, so I won't go into detail. It's something that we have developed in ESA-Lab about a year ago called Major Tom, and there's no magic trickster. It's just pre-processing of data and making it easily accessible for free for anyone to use. So that just seems to work. If you just upload a lot of data that is in the format that the AI experts will expect them to be in, you will see a lot of things happening. So by now, I just checked the last statistics. This is a statistic over the last month. We have thousands of downloads of Major Tom datasets just because it's the fastest way to get a nice pool of Sentinel-2, Sentinel-1, and digital elevation model data, and soon probably a few more modalities. So what does it mean fast and easy access. It just means that you can plug this into your Python code that download the entire dataset without worrying about anything else, so that you can focus on building models, right? So with that, we keep seeing more and more models popping up that are relying on Major Tom, just because this whole stage of assembling data, curating data, is now gone, at least within the context of these models. And the developers can focus on the most interesting stuff, which is new models, new techniques, and new capabilities. Right, so one example is as a recent work of, again, from a research visit of Miguel Espinosa in ESA-Lab, which was developed in only 1 month, just because we had already access to all of the data. So if you go to the QR code, you can actually try the model instantly on your mobile for your own. And what you will see is that if you just click generate in the top of the app, you will see a fake sample of Sentinel-2, L2A, L1C, Sentinel-1 RTC, and digital elevation model. What you can do as well is you can just condition on any subset of the modalities to generate the rest, right? So there's another fake sample that's conditioned on the Sentinel-2 data, right? Another thing you can do if you have very fast access to Major Tom that's already on Hugging Face is that you can take a real sample from the catalog. So this is, in fact, data that has been captured by the satellite. And what we can do with that is, if we didn't have our Sentinel L2A processor, we could try to use the same model to apply atmospheric correction, and we could, at the same time, we could also maybe approximate the digital elevation model for a sample. And that seems to work. It's a very prototype model, but it's been only developed within a few weeks. So that just shows the power of making data accessible and easy to ingest for users who want to focus on their real work. So another example is a collaboration between ESA-Lab and Adobe, where we map text. And again, we use a diffusion model to condition on text to generate 2.5D representations of terrain. Again, using the exact same data, but in a very different setting, where the main purpose is to empower the creative industry to generate terrains quickly that they can use in their assets. And again, there's an app on Hugging Face, which means you can immediately try the model for yourself, see if it's bad, see if it's good, see what could be better, and immediately get an idea whether you like the model or not, or maybe you want to build something else. So that was AI-ready data. Now, what happens when we actually have models that can interpret our data at scale? Well, that goes back in the loop, and we can think of improving our infrastructure with the advancements made in the context of AI. So what we've done very recently with ESA-Lab, Cloudflare, and now Asterisk Labs is we just started computing a lot of embeddings. And the main reason here is that before we actually evaluate which models are most suitable for embeddings, which are the most promising use cases for embeddings in the coming months, we need to make this data easily accessible for everyone. So now, again, without taking a few months of computing all of the Major Tom samples with deep neural networks, you don't have to do that as a user. You can just get the output representations from each model and see exactly what you can do with the embeddings and whether they are of any use to you. So again, this is the same approach of just making the friction between the user and the data access as low as possible. And again, it's the same line of code. You can just put that in your Python code and download the entire dataset immediately. Okay, that's about me. So now I just would like to make a quick announcement. So all of these contexts will be covered in the upcoming Copernicus AI report that we will deliver as Asterisk Labs for ESA. So what we want to do is a lot of the same context with AI landscape assessment, the data infrastructure, and so on. But most importantly, we will want to acquire quite a lot of input from the community and feedback. So if you have any ideas for how we can do a better job preparing the report, which will be used for the stakeholders and many maybe non-experts, people who don't develop the models like Miguel, we would really love your feedback, because this might turn out to be a very useful document that we will use in the coming years. So feel free to contact us at hello@asterisk.com. Feel free to reach us at ESA Living Planet Symposium, and feel free to submit to Terabyte's workshop at ICML 2025, which will cover a lot of the topics I have listed in this talk. So I think that's about me. I really thank you for your attention. And if you have any questions, feel free to reach me or just go to hello@asterisk.com.
Thank you. Is there any question in the audience? Yes, please. We have.
Hi, thanks, Miko. Great presentation. I wanted to ask, out of curiosity, about the robustness outside of the Copernicus. If you tried to embed different data providers with the Copernicus embeddings, and whether you got something meaningless or meaningful.
I mean, at a certain scale, you always get something meaningful if you just compute a function over a very large set of data. So it will usually have some value, probably. At the same time, all of the models we've used are models designed for Copernicus data. And I mean, in many cases, they will just not be possible to apply to other sources of data. So it'll be quite interesting. But I think an interesting point here is that if we make the data accessible, we get so many models that work for Copernicus. There's not many other sources that get this type of community. So that makes it a bit harder to find powerful foundation models for other data sources, just because it's so hard to access the data. But as soon as you open up the data, you just see people that you weren't even aware of build models for you that you can later use and maybe make your infrastructure more powerful.
Thank you. There's one more question in the back.
Yeah, thank you for this great talk. So in my experience, one thing that you encounter if you actually want to build applications is that, of course, machine learning ready data is the important thing to do the training, but for inference, you typically need, right, you don't have the data set prepared. So what you actually need is the exact code that you use to, right, you need to ensure consistency between the data in your inference setting and your training setting. So what you actually need is the code to actually reproduce this in inference. So is that also available for kind of how you get to the machine learning ready training data set so that you can actually replicate it in inference?
Yeah, that's a great point. And I didn't want to flood the presentation with links, but we have a GitHub repo with all major term code for how to build the actual data set, how it's processed, and so on. We do have a preprint that describes, not a preprint, a conference paper from last year's IGERS that described the process exactly. But it's, I mean, this major tom is, again, also maybe some form of prototype. Like, there's probably still things that we need to figure out as a community, how to like find the right format for scaled up data, for even for Copernicus, right? So the chances are that we will need to develop something even better in the coming years based on the feedback that we get. And again, we will have to release all of the code openly so that people are aware of how that relates to their own inference pipeline. But inference is absolutely crucial, and this is a context that will be covered in the report.
Excellent. Thank you again, Mikolai. I think we're going to stop here, and I'd like to thank to all the speakers from the session. Thanks again to everyone.
Thank you.
So now it's time for the reports from all the sessions.
Okay, it's time. Oh, hold on. Yeah. It's already there. It's okay. We did the translation. Okay, thanks for still being here after 3 days of long discussion, 2.5. It will be the time for the closure of this workshop. Before to do this wrap-up by each session chair, we'd like to do some announcements, and then we'll deep dive in the wrap-up. So please, Christian, the floor is yours. The idea is to present you some kind of way as well to collaborate with the PhilLab. And we have to do it now because of agenda conflict. Thanks.
Okay, thank you, Nicolas, and hi to everybody. I would like to spend this 5 minutes opportunity to present, introduce you the ESA-FI Lab Collaborative Innovation Network, which is a great initiative led by ESA-FI Lab, and might be interested all of you. And so, what is the CIN? I'm Cristiano, I'm a physicist and lead scientist at PySchool. You already met PySchool early this morning, and you will meet again us in the afternoon for the hands-on session on the Earth Virtual Expert. But now I would like to spend some words on this. And this Collaborative Innovation Network is basically led by FI Lab and managed by PySchool. And what is the CIN? So it's a dynamic community that aims to bring together leading researcher and innovative talents to harness transformative technologies and transformation in Earth observation sector. So again, I use emerging technologies like AI, quantum computing, quantum technology, high-performance computing to, you see, accelerate the future of Earth observation. So the ESA-FI Lab Collaborative Innovation Network aims to establish a global network where researcher and innovation can collaborate together and collaborate with ESA-FI Lab, and sharing, obviously, knowledge regarding emerging technologies and Earth observation more in general. And you see, basically, who are the person we are targeting? There are PhD students, postdoc, researcher, but also visiting professor or visiting expert from the industry that would like to get in contact, to collaborate with ESA-FI Labs on these specific topics. And we have about 50 grants for the next 12 months to, you see, start this collaboration and this opportunity. And again, at the Collaborative Innovation Network, we are also organizing events, workshop. In the last workshop, last March, we invited the two leading experts in high-performance computing, Professor Piotr Lucek from Tennessee University, which is a leading expert in HPC benchmarking, and also a senior software engineer from NVIDIA that basically gave us a workshop on how to use in an optimized way NVIDIA HPC tools. And we are planning to organizing even more on specific topics like quantum computing, quantum error correction, quantum sensing, HPC, so on and so forth, and obviously foundation model and AI. So again, I finished. I suggest you to follow the LinkedIn page of the Collaborative Innovation Network, where we are going to share all the initiatives we are planning in collaboration with ESA-FI Lab. And there are also some open calls for PhDs, postdoc, visiting researcher to join, and also visiting professor to join ESA-FI Lab and work on, guys, this topic we are talking about in these days. So thank you again, and I leave the floor again to Nicolas.
Thank you very much, Cristiano. Okay, let's move to the wrap-up by the different session chairs. So, yeah, I guess next is Thomas and Amen. Over to you.
All right. Yes, we had the pleasure to, together with Hamid, it was great kind of to chair the two sessions, latest advances in AI foundation models. So it was great to see the momentum this year. Going beyond single modal foundation models, going into the multimodality and also the sensor agnostic architectures. And in particular, also kind of thinking about scalable modeling. So, and I think, you know, in the future, we'll hopefully also see kind of how we get these models out in operational mode. The sessions also highlighted both methodological innovations as well as practical applications. So, you know, how are these foundation models becoming useful? And from our side, the highlights were on the model architecture side, mainly kind of mixed modality models, as well as vision language models for EO. So from the mixed modality models, we've seen many different architectures taking advantage of mask autoencoding with different strategies, AUX MAE, mix MAE, as well as kind of the AnySat and OmniSat and then Terramine to mention. From the vision language model side, so there's the release of GeoLang Bind, a vision language model trained on 2 million image text pairs, and the GeoVIT for temporal spatial progressive learning. But then going beyond kind of discrete modalities, there's kind of the intention kind of to adapt to the different sensors, including sensor and acquisition awareness. Basically, several talks talked about architectures that explicitly encode and adapt to the sensor characteristics. So there we see some approaches like SA-MAE, SENPA-MAE, and SAR-FORMO. So where sensor information is injected as an additional parameter, and we see projected spectra kind of to really cope with the full range of the spectrum. So I think these are really promising advances, and with this I'd like to hand over to Amit.
Yeah, and then the next theme was on the scalability. So we had several efforts that ranged from looking at like massive model pre-training, and almost many of the models do, but very specific ones, but also thought about, okay, how do we do it in a light way for fine-tuning, becoming more prevalent so everybody can access them, and also pruning strategies. One of the examples was the MapX one, which introduced the modality-aware pruning of experts to make sure when you have different modes in the inference time, you can do the right fine-tuning basically, but in the pre-training stage, you can benefit from the multimodality. And also one specific one was on the understanding of redundancy. So thinking about the differences between images in the Earth observation compared to computer vision, what are the redundancies there, and how we can explore that, not just basically leave it there in pre-training and in fine-tuning, particularly in the VIT structure, which is one of the dominant structures we saw across all of these. In terms of what is coming next among the different like recommendations, future directions, and everything that everybody talked about, there is a shared understanding of a truly multidimensional model, meaning multi-temporal, multimodality, multi-sensor, but also thinking about potentially fusing Earth observation and weather and climate models. We saw shared themes across all of them that can also then represent these processes, thinking about biological processes, phenological, atmospheric, and others. So they're going in parallel, but there is a synergy that they're coming together. So we hope to see those in future. Also, edge deployment of these foundation models. So when it comes to usability, edge meaning the phone, the drone, the satellite itself, how we can deploy them, coming back to the scalability and efficiency. And last but not least, operationalizing these for decision making. So going beyond the research phase of these models that has been a very rapid cycle, we all know, coming to a place that these are deployed for decision making and societal benefit, basically. Well, that's all from our side.
Thanks a lot. Next, there will be the one on advanced senior science, weather prediction, climate using foundational. Floor is yours, Sujit.
Yep. Hey guys, again, I'm Sujit, and I'm Gustavo as well. I don't know if he's here. So we'll go ahead with the summary.
You have to click.
Oh. Yeah, so we had a session, and so it was showcasing the foundation models and Earth observation. We had things in the weather and climate applications as well as also we saw a lot of self-supervised learning methods and people trying to utilize it and explain it from the physics perspective, that will the model learn convection, conduction, does it follow partial differential equation or not? And the speakers emphasize advances in the accuracy, scalability, and physical interpretation of all of the FM models. So we have a broader trend towards operational real-time high resolution. Now, speaking of that, there is one point that I would like to bring, that we saw actually a lot of people building the foundation model through the different architecture. One thing I would like to specifically highlight that the foundation model is truly foundational because if you create one or two and other people can use it for their own downstream application. It felt a bit of a competitive landscape, which I would encourage people not to go into, because this is not a computer vision domain that we are fighting for, or CVPR papers, right? So it's better that if we use a couple of foundation models already present in the domain, and you use it on multiple downstream applications and evaluation, and see how they can be improved. Because all of the different architectures have their own benefits and own lag points. You can make them better on the basis of injections technique and adaptation techniques. Based on that, we saw foundation models for EO and climate which are maturing. We were having this talk before, and I see them to be plateauing really quickly, and it is heavily dependent on the computer vision domain advancing through these architectures, because major things are adaptation from the computer vision domain of these infrastructures of the foundation models, architectures, backbones, and other stuff. So you have multiple studies demonstrating operational applications. We have also seen the multimodality is one of the key aspects people are trying on. Obviously, you cannot just deal with optical data or SAR data. There are a lot of applications where the people are more reliant on just the point data measurement. So what do we do about that? How do we infuse all of this information? Then self-supervised, obviously, is an efficient learning technique. There has been a bit of discussion on pretext task, but commonly the people had the pretext task of the reconstruction of the masking technique. Which also bring forth the objective of people trying different questions on pretext objective, that what all can be worked, rather than just using the masking approaches and the spatial reconstruction. And the fourth, which was the most important part, which I felt like was the validation through physics and real-world impacts. So how do you validate that these models are better? Do you actually care about that the model performs 80% on a task and compared to 80.5% on another task, or through one model or other? Does 0.5% matters to you a lot compared to does this model explains the physics or the phenomenon that you're trying to address? Does the model understand the change or evolution of state spaces? So the common theme that we saw generally emerging in these things is the general purpose AI for EO and weather and climate, which is clear movement towards universal FM capability of generalizing across tasks, regions, and timescales. Fusion of physics and data-driven models, so try to combine machine learning with physical knowledge, either through hybrid modeling or enforcing physical constraint, like radius transfer, hydrology. I think I clearly remember one of the presentations trying to use Fourier transforms as using as a loss function, and also a couple of pins method to use the loss function. So what is the implication of that by making the model less generalizable or more generalizable? We had good amount of questions around the VIT, diffusion, swim backbone approaches, and how to validate them scientifically, and the change detection, encoder design, specific loss functions. The major takeaways from the session was that we have to invest in multi-sensor, multi-resolution training pipelines, because I think we have plateaued somewhere around using a single modality there, and it's because we are using the similar VIT backbone, swim backbone, or something very similar architectures from the transformer. One specific aspect I think people have not tried here in this domain, which I can highlight to you, is you guys can also try state space models. I know nobody has tried that in this domain yet, but they have a very long contextual sequences that can be modeled. It could be a very good experimentation to be see when you model something without the attention. So attention is not all you need, sort of situation, right? So that is there. Then you have the optical, SAR, gravimeter layer data. We have the advances in real-time and adaptive systems, and then bridging the research and operational use, because all of these models, some of them are really large, like, for example, WXC at 2.3 billion parameters. Prithvi EO is 200. The other people have 300 million. The other people had 300 million or 200 million parameter models. So how do you use this model in operational situations? How do you fine-tune them, use it through the adapters, or fine-tuning a couple of layers and other stuff? Thank you.
Thank you. We move next to the computational challenge in training, running large-scale foundation model. Yeah, Gabriele.
Yeah, thank you, Nicolas. So I will be quick regarding this session. So when we set it up, I had in my mind a different, let's say, or like a different set of submission that I was going to see, but actually this is actually good, because then we have community responding and we can actually take the pulse of what is actually going on. So basically what we can say is that the session has been mostly focused on placing these models in an operational setup. So basically I try to find strategy to really make them adaptable for in-operational tasks. And so basically focusing on efficient fine-tuning, for example, strategy, novel distillation. So really try to basically go smaller and go in an operational setup. There were like different techniques exposed, different type of framework, but very relevant, let's say, was the onboard satellite processing, so edge computing. So we have, as I said, we have a focus on scaling down, then scaling up. We had edge computing. There was, I would say, no HPC in a way represented. So maybe next year, or if there will be a new, let's say, edition of this workshop, probably we might see also that part. Yeah, adaptation and basically everything to circumvent the computational challenges. So we have seen some trends or some ideas, like for example, head only for fine-tuning or different knowledge distillation as an alternative approach. We have again seen different scenarios like edge and onboard computing. So in terms of discussion, so we have some discussion in the round of generalizability for the learning weights and embedding, so how actually this can really work in a general scenario, also when compared to how the main training was done. Data compute efficiency questions, that also was exposed. And also let's say, the way how we can move these models on a more even less, or like with higher requirements in terms of hardware. I see, future direction. As I presented before, the HPC is a variable is for the community. So I hope that we could see also the community engaging more with these computing facilities to do. Maybe not as Sujit mentioned, not everyone has to do a foundation model, but you can still use this technology to do many other things. And this also goes to my last comment, where basically I just come back to the statistic, and we were like the session with less, let's say, submissions. So let's see for the future. Thank you very much.
Thank you. Thank you very much, Gabriele. Next one is about datasets benchmarking and evaluation of foundation model in EO with Paolo and Nicolas.
Hi, everyone. Disclaimer, the slides are not as polished as the others. But yeah, it was a very interesting session spanning, we have 3 different topics there, almost related, but kind of different. And we identified, in the summary, established frameworks for benchmarking that has been described, like GeoBench, Pangea, FiliOBench, that kind of follow very similar philosophy. Then it was very interesting to see other ways of benchmarking, this concept of exploring the embedding space, for example, GFM bench, the confidence and certainty quantifications on predictions. And it was really interesting to see also someone thinking almost completely out of the box and applying this concept of almost meta-analysis that is used in the medical domain to results from papers on different GFMs to rank and predict scores on new data sets. And then there was a couple of contributions around real-world applications that were flagging up the different requirements for benchmarking that goes around actually deploying things. Was mentioned on the edge as well. So.
Okay, so yes, so regarding key highlights, there were 2 sessions. So you had 2 sessions on Monday and then on Tuesday, datasets benchmarking and evaluation. There were many highlights. I think, yeah, one of the interesting questions were that why do you develop like both GeoBench and Pangea? And the answer was that they were developed at the same time. So there are many evaluation frameworks like GeoBench, Pangea, FiliOBench, also Copernicus Bench. There is also Hamed from Clark University also presented an evaluation framework for evaluating foundation models before the downstream task. Regarding other key highlights, the Allen Institute, so the Allen Institute for Artificial Intelligence, they also said that they will release Helios, so a Helios foundation model, multimodal foundation model. And yeah, there were very many different highlights, and Paolo can continue.
Yeah, so here's more research questions or themes emerging through research questions. There were this question around how many benchmarks we need, what's the point of developing a new one, and so on. But how accessible actually they are in terms of computation, in terms of resources, in terms of ease of use. How can we also better interpret what models to learn and how confident they are on predictions? This was another theme that came out. And around uncertainty. I think there were many nice and interesting interactions between the audience, the presenters. There was one that probably a lot of people would expect around what is the point of FMs if performance is very similar to a custom UNet. I think we have seen with some models that this is not entirely true. Is most often than not true if you unfreeze the backbone. So it's an evolving field, and it's, I guess, responsibility of everyone in this room to keep pushing to improve what we can do. And then this concept about meta-analysis was really interesting, and how can we interpret, how can we trust what comes out from this ranking if no actual experiment has been done on a new data set, for example. In terms of key takeaways, benchmarks have to be accessible, reproducible, and give researchers and practitioners, because we're also doing this for the actual use in real world, actionable insights. Explainability of models' predictions is extremely important. And then pre-training and benchmarking data sets require high-quality, multi-sensor, multimodal data that will help us building better models, but evaluating better also what the models learned. And yeah, really good quality contributions and interesting discussions is my comment. Thank you.
Thank you very much. Then we move to adapting foundation model to geospatial data and specific geotask, from adaptation to adoption of foundation model for you. Ahmed and Anna, please.
Yeah, so this session, as the name very accurately depicts, was focusing on advances to combine a bit more of the nuance that we have in satellite data, so specifically different data types, modalities, resolutions, temporal information, and so on. And we had a really broad range of presentations that sort of included more methodological advances and figuring out how we can improve architectures to better handle that nuance, but also looking at how we can better interface with off-the-shelf existing pre-trained models for these applications, and reviews opportunities, limitations, etc., of current approaches and what we should be paying attention to. And specifically, I guess the key presentations and highlights that really stood out is a lot of work on denoising and gap filling, often looking at shadows and clouds, which is, of course, a common problem, working with optical data in particular. And then, as we've mentioned, methodological advancements, so looking at how mass autoencoders, I guess, primarily stood out in this session, need to be adapted, and at what point we fuse information of different modalities, etc. Including temporal information, that's still a point of discussion, and as we've mentioned before, this sort of emphasis on building models that understand the nuance and the realities of the data that we're working with a little bit more. And we had a great presentation on SAR, which of course is a very complex, there's lots of complex data products that are derived from SAR sensors that deserve a little bit more love and attention than sort of the just throw it at the model and see what sticks. A couple of works were presented on combining vision and language, which of course is an ongoing topic of research to specifically figure out how language can help in an Earth observation context. And then the detection of rare events. How sensitive are these models to detecting change? What change is too small for them to pick up on, and how we can use embeddings to make sense of that. And so just to summarize it again, the common themes and emerging trends that really stood out in this session were these modality-specific adaptations, so coming up with architectures that better represent the physical realities of the sensors and systems that we're working with. In terms of architectures in our sessions, the models that stood out are diffusion models and masked autoencoders. I mean, specifically masked autoencoders, I think have been discussed extensively across the last couple of days. And this idea of, fusion of data, but also generalizability of the models. How well do they work in areas that they haven't been trained on before? I think that's a really important area of research for all of us to talk about, especially as we're trying to combine Earth observation data with maybe more in situ samples that are inevitably not available everywhere. So these foundation models can really help us make sense of that, but we need to answer a lot of the questions on spatial generalizability as well. And of course, as our colleagues have just talked about, benchmarking and reproducibility are becoming more and more important.
Sorry, you have to see me twice. So on the kind of audience engagement, there are particularly two topics that was brought up. One is in terms of the augmentations. Some of the practices are we just keep augmentation practices from computer science type of things. What if they are physically inconsistent with basically the physics of the Earth observation, and does it matter? There was some discussion in one of the presentation at least, and the short answer from our discussion was yes, particularly if it basically you want to create models that eventually understand the physics, those augmentations can be helpful. But it seems to be an area that needs further expansion and research. The other one was what is basically the benefit of this for all of these pre-training, and I think Sujit brought it up as well, compared to simpler models that are designed from scratch, trained from scratch for a specific case. And this is where we need more exploration. As much as the benchmark scenes, the F1 scores, the IUUs are helpful, we need to see maps, and I think Robert brought that up as well in his presentation. As much as this is an AI conference, it's also an Earth observation conference, and it would be good to see predictions from those models in a map. What does it do with above ground biomass? What does it do with land cover? What does it do with water body classification? My personal reflection, we didn't see that many maps, and I was a bit surprised, honestly. So hopefully we'll come to a point that in future we see more of those at least. Some key takeaways and recommendations. The custom EO foundation models, that was one of the discussions, outperform off-the-shelf models that are usually trained on like computer vision type of models, and I think that was a shared thing, particularly when they're adapted to the modalities and the resolution of the data that we have. Diffusion models and MAEs seems to be very promising for self-supervised. And I think I have a typo there. That is for SAR, not synthetic data augmentation. That is my bad. In Earth observation, and is a common theme again. Many presentations, many models are using that architecture. Certainly, multi-resolution, multimodal fusion strategies should be matched to the task and the data characteristics. And there is an area of research again there. We saw some of the early fusion, late fusion type of things. The kind of final comments from us as session chairs, I think we saw a good amount of these advancements, and foundation model research community being more aligned, having these forums to talk, with a shared interest in creating those robust and open source and task-aware tools. Because at the end, we care about solving problems. So it is good to see that direction and alignment. And with that, yeah, we're happy to. Thank you.
Thank you very much. Now it's time for the highlight on the embedding, geospatial semantic data mining, and data volume reduction with Vegu.
Yeah. Hi, everyone. So in our session, unlike the other sessions, we talk on learning-based compression and compressed domain analysis, and also how we can store and distribute the embeddings, and what are the importance of these for the scalable data analytics. In addition, we address the topics on parameter-efficient model adaptation, specifically using optimal transport techniques, and also synthetic data generation and its impact on large-scale training to address data scarcity. And also one important topic that we discuss is the integration of physical models, so physics-guided model training that can help to guide the foundation models to be more specific to Earth observation downstream tasks. And in average, so in summary, I can say that all the discussions highlighted the importance of scalable, adaptable, efficient, and physics-guided next-generation EO analytics integrated within the foundation models. Okay. Okay, emerging trends. physics-guided model training, model development. So it was also highlighted that we need to be very careful what we call for multimodal, multi-sensor. So the first speaker emphasizes that just grouping image bands to subgroups and calling them as different modality is not the right way in remote sensing. And if we are talking about multi-sensor data, it can be considered as multispectral or multispectral very high resolution, multispectral high resolution, low resolution, or synthetic aperture radar data, or hyperspectral, or so on and so forth. So we need to be very careful on that. And also, there was a suggestion on thinking about how these models can be modeled given the EO data characteristics, so not just applying computer vision models for remote sensing data analytics, but putting on board domain expertise. So for the learning-based compression, it was shown that results are much better with respect to those obtained using traditional compression models like JPEG 2000. I should admit that learning-based compression is a hot topic now in remote sensing community, and there are already several models existing that include transformers, autoencoders, GANs, diffusion models, so on and so forth. And the research goes in the direction of how the existing models in machine learning and computer vision communities can be adapted to address spatial and spectral redundancies, so spatial and spectral compression, which is very important, especially when you are dealing with hyperspectral data. And there were discussions on if the video compression algorithms can be relevant in remote sensing to include also the temporal content. So let's say that in summary, if it is about learning-based compression, spatial, spectral, and temporal dimension can be relevant to address the redundancies and to compress them. Okay, so so how to store and distribute the embeddings can be very relevant for the scalable data analytics. But I should admit that that is not new. So the existing search engines, particularly those operating at the image level, they already index the image content. And the most popular way is to use hashing. But I think that is the right direction if you are considering AI assistant, search engines direction. And then discussion points were like, what could be the best compression rate, given the real application scenarios. So there can be also approaches that are like adaptable compression rates that can consider it adaptively. One way can be to use explainable AI, so maybe explanations can tell us which are the less relevant parts of the image, and then it can allow us to have adaptable compression ratio for the, with respect to the image content. Then it is very important to move to the directions of physics-guided models and the questions that we discuss on how to integrate physics into the models. And then we discuss about generalizability and representativeness of the synthetic geospatial data for the real applications. Recommendations. It is very important, of course, as we have also heard from the other summaries, it is important to focus on efficient model training, scalable model training, and if you are interested in compression, it is important to consider spatial spectral redundancies together instead of just applying the compression models that operate on single image band at 2D level. And parameter efficient adaptation has been talked several times, so that is definitely important. Most of the adapters existing at the moment, they are specifically designed for different tasks, but it is also important if the foundation model is trained on single date on just few time steps, how we can adapt it for long time series data, because it is quite difficult to train a foundation model on the long time series data, but if your downstream task is on that, we need special adapters for that. So I think I missed that in this talk, so maybe in the, as a future work, one can consider this. And yeah, so this is all from our session. Yes, thank you very much.
Thanks a lot. Now I invite on stage Robert for the session around downstream use case and commercial application. Over to you.
Is it just me? It's just me. Okay.
Yeah, I think so.
But it wasn't just me. But are we the last? No, we've got several more, right? Am I the last one?
No, there's
Okay, good. We were the last ones last night. Thank you, everyone, for being here to the bitter end last night. That was wonderful. I'll be really quick. So this was a very applied session. I found it super interesting as an applied person who's not a computer scientist, but demonstrating real-world applications, foundation models in both commercial and public sort of examples. So we saw foundation models being used successfully and also sort of experimentally, and that the constraints and challenges of the real world actually pose, nice opportunities for sort of innovation, but also real world constraints, and can be a substantial component of what has to be dealt with. So we had 6 talks, so I tried to get everybody's name in here. Hi, everyone who's in our session. Excuse me. So we saw some examples of non-image-based foundation models, which I thought was really cool for me. Maybe all of you know this, but including tabular data as well as graph neural networks. We saw examples of testing the model infrastructures in real-world situations, so with weather data, with high-resolution imagery, with land cover in coastal zones. So those were different points along the continuum of how operational those are. And then again on those constraints, so examples where having to do the vision transformer ideally in a situation where you've got a commercial application, you've got high cost imagery, can we use that to make that better, quicker, cheaper? How do we deal with the real world constraints of having training data that's not co-registered? That was one of our talks. Sort of an experimental version of using Prithvi in a cloud detection near real-time example. And then for training data for land cover labeling, how much can we actually use this? Because that's a very expensive process. Can these be used to sort of augment the human component? So, not surprisingly in this audience, we see promise in foundation models. Again, I was really interested in the non-image-based approaches, which are effective, and probably we could be thinking of these as alternative tools in certain use cases. However, and this was appealing as a remote sensing person, it is still useful and necessary to think about the pre-steps in a lot of this, in these workflows. An interesting question, we do see this, and Sujit mentioned this as well, different models are in fact different in their abilities. Should we be really trying to, I know this is heretical to say, but to use one foundation model for every situation. So there are hierarchical approaches we could think of as well. And sort of comprehensive and fair benchmarking across different foundation models would certainly be useful to us as those of us who are in more the user community. And that's it.
Thanks a lot. Last session to be presented about Agent AI, Agentic, Digital Assistant, and LLM. Kumar, thanks.
Hey, thank you. This is the joint session between me, Kumar, and Nikolai. It was an interesting session. The session explored how LLMs and generative AI can help advancing Earth observation, and in a general sense also applicable to scientific research and applications within science as well. We touched on topics like how LLM-based tools can be used to to improve data accessibility, automate workflows around data access and contextualizing with maps, with literature, with EO workflows, and how we can tie them all together using agents as well. So that's the overall session theme. Some of the key presentation, I tried to group them together. We saw a lot of open source tools and models, and a lot of open source APIs and interfaces for all user levels. There were some use of closed source models, the famous ones like OpenAI's models, but they were used for LLM as judge use cases, which is also for some reason prevalent in the general scientific community as well, which is fine. There were some, there were a lot of, more than half of what we were presented were all about natural language interaction to make EO data and APIs understandable through plain language, which is good. And we also saw adaptation of LLMs to EO by adapting using domain-specific LLMs. EO was a use case. We saw some presentation today in the morning. We also saw some rules for establishing scientific guardrails as well. So we saw some multi-agent architectures. There were a few examples of that in the presentations, in the session as well. And there were some LLM assistants which used retrieval-based chat interface for data discovery and analysis. EOAI from ESA was an example. And we had several RAG retrieval augmented generation architectures which integrated external knowledge, specifically EO indices to make AI insights clearer and more relevant. And finally, last but not least, we saw open LLM inference server, Blabber, which is provided by JSC and Alex, which is a privacy-oriented open source LLM to host and serve open source models. So the themes and emerging trends for the session included lots of natural language interfaces. Most of them are naturally chatbots and assistants to make EO data tools accessible to non-experts. Lowers the barrier to entry for scientific data use and analysis, which is good. Several systems had multi-agent frameworks to coordinate tasks like data ingestion, model training, result interpretation. Then there is increased multimodal RAG utility, which is multimodal is a keyword here, where we combine text, imagery, metadata, API, and external knowledge into one system, which is good to see, and I would like to see more in the multimodal RAG direction. Some discussion points around audience engagement here. We saw some concerns on licensing around the Llama family of models, which is the most prominent open source family of models. Llama specifically fails to provide freedom to use models for any purpose, which is a problematic use case for open sourcing. But there are other open source better models available, as pointed out by the conversation that we had. There is also limited generalization capability of the automated EO workflow systems in the sense that when we are working on agents, these agents are specialized in single purpose. And when we are building a system out of it, the system by nature can only provide a specific set of tools and services that can only do specific set of things. So there is an inherent limitation on what the tool is capable of. And for EO, where we want to have a larger complex reasoning, long-tail dependency capabilities, where we want to chain multiple tasks and complex reasoning tasks, that is a problem, and it is relatively unexplored area in the session. So some key takeaways and recommendations. Tailored LLMs observation is a good direction. We should focus on more pre-training data sets and benchmarks, more importantly, to improve and evaluate model performance, and also in general scientific context. Multi-agent architecture are making data more accessible, which is good. We should prioritize interoperability, modularity when we are creating these multi-agent architectures. Also, EO-guided reasoning as well as part of the multi-agent architecture as well, and user experience to support a broader adoption into the EO community. Some additional comments. We had a very limited community so far, only 6 talks plus 2 posters. We would like to see more interaction and community building around this. There is a few work definitely that is needed in this community, and we would like to see more engagement. Some unexplored areas still exist. We would like some deeper discussion on AI alignment, specifically for EO. Reinforcement learning, specifically for when it comes to multimodal or multi-agent workflow, we would need to consider reinforcement learning as a way to guide the long tail or solve the long tail dependency problems. Say one task is dependent on another task that is, say, thousands of tokens or 10,000s of tokens or millions of tokens before, then we need to solve it by the way of using reinforcement learning. And we need to also talk about guardrails, and guardrails specific for science, and then guardrails specific for EO, and create a framework for it, create a discussion around it, and talk more on it as well. And also establish domain evaluation and build on top of what's already existing on EO data, or domain evaluation for EO data specifically for LLMs as well. And there are some talk also needed on AI safety with EO focus. And also, finally, I'd like to conclude by asking support for EO API function calling as well on the language modeling. So, yeah, that's the conclusion for this session. Thank you.
Thanks a lot. Perfect. So yeah, it's time to move to the very closing words. So we have just 10 minutes to go before lunch, I guess. A few announcements. Thursday, Friday this week, there will be another workshop on AI resilience and disaster response. So I just invite on stage Monique that will give a quick highlight on this workshop that will be happening for the rest of the week. So yeah, if you have the time to stay in Frascati, yeah, please.
Okay. There we go. Okay. Thank you very much. I know that things are winding down, so I'm going to try to keep this short and sweet. First of all, thank you so much for the opportunity to participate in this really enlightening and inspiring 3-day workshop. I think we can all agree that foundational models are not only the present of AI and EO, but also are going to be a big part of the future. So it was a real privilege to learn about the state of the art, also the opportunities and challenges from leaders in this field. My name is Monique Koglich, and I'm the Innovation Manager at Fraunhofer Heinrich Hertz Institute in Berlin. And I also serve as chair of the Global Initiative on Resilience to Natural Hazards through AI Solutions, which is a partnership between 5 UN organizations: the International Telecommunications Union, World Meteorological Organization, UN Environment, UN Framework for Climate Change, and also Universal Postal Union. The global initiative, which builds on the outcomes of a 3-year focus group, is laying the groundwork for international standards in the use of AI, and that includes foundational models in disaster management. Now, international standards are really critical for the responsible use of AI, and as we state in our October 2024 Nature piece, AI tools that are created in the absence of international standards could have a variety of problems, including not being compatible with each other or interoperable with each other. And because disasters can move across borders, this could be a lost opportunity for continuous early warning coverage. Developing such guidelines, however, is a mammoth task, and on a global scale, we need to keep abreast of the newest advances of AI technology in this domain. We need to consider end user needs, and we need to liaise with policymakers from the ITU member states to develop scientifically sound guidance that's also accessible for a non-scientific audience. Thus far, as a community, we've produced a collection of technical reports, including a standards roadmap and a glossary. We've produced a series of educational and capacity sharing activities, from workshops, such as the event that we're going to be organizing tomorrow, hackathons and challenges, open access publications, and even hands-on training sessions. And we've also secured Horizon Europe funding for 2 projects related to our work. One is called Medusa, which is building a multi-hazard early warning system for the Mediterranean, applying AI. And another one, which just got accepted, we're very excited about, is called Artemis, and it's going to be an alert and impact forecast standard for emergency management project. These achievements were made possible by close collaboration with leading organizations at the intersection of AI and disaster management, such as ESA and NASA, as well as the dedication of a community of experts. And please take this as an open welcome to contribute to our work. It's exactly experts such as yourself who are actively using AI foundational models that we need to support this effort. So we're honored to have our next workshop and meeting of the Global Initiative immediately following this event. And I hope that you'll join us tomorrow and Friday. We're going to be on site, but you can also participate online in case you're already headed to your next destination. And I just want to mention that registration is possible over the QR code. And to help our colleagues at the ITU to organize, we would be very grateful if you would register by 3 p.m. today, because we need to get those final numbers. So thank you very much for your attention.
Thanks a lot, Monique. Well, again, basic stuff. I mean, if you like, again, to work with us at ESA Philab, there are different ways. You can collaborate as visiting researcher. You can be also visiting professors. Yeah, this one, sorry. Well, also you can bid to the invitation to Thunder that we are issuing. Well, I don't know what's going on. So there's many ways to work with us, either funded or not funded. So please come back to us if you have any question, if you are like a young student willing to be a bit living in Italy for a while, let us know, and then we'll be happy to welcome you for a while. Well, with that, just some information about this afternoon. So this afternoon we'll have the hands-on session for those that registered for it. There will be one on geospatial foundation model with Prithvi and TerraMind that will be happening in the Magellan. The Magellan can host about 100 persons. We limit it to 50 persons, the number of persons that will get access to the credential with, let's say, environment. But yeah, even though you didn't register for it, you can still attend, like, let's say, in the back of the room, and maybe attend at least the presentation passively, let's say. So you are free to join this one. For those that register, you need to get your credential. So please get to the reception desk. We will give you like a page with the printed login and password for this afternoon session. At 2:30, we'll come back here. There will be about 30 minutes talk about environment, getting access to the environment, let's say. So please attend, and then we'll be dispatched in 3 different rooms. So the Magellan, the James Cook, which is nearby the Magellan, and the 15111, the famous one nearby the gym. So yeah. Some other information, yes. I've heard about some frustration because we decided to organize parallel session and everything, so you might be some kind of frustrated to not be able to attend all the talks. So everything will be put online after the event, so the recording, the slides, and also the digital poster. So there will be some email asking you permission to do that, and also if you like to provide the digital poster, everything will be on the website, so please stay tuned a bit. I mean, it will be done in the coming weeks, months, let's say. With that, well, I'd like to thank all the co-organizers of this event. I mean, you see them listed here. So Giuseppe, Anca, Clément, Raoul, also helping from NASA side, Sengda and Kevin, and for all the logistics, Francesca. So please applaud them because they did a very tremendous work. So please join me. And especially Francesca that did all the heavy lifting about logistics and stuff like that. So thanks. I'd like as well to thank all the people that helped for setting the program. So there were a set of reviewers. Actually, you submitted your abstract, then there was at least 2-3 reviewers per abstract. So this is the so-called scientific community. And based on that, the program committee decided for which were the one accepted for the oral, which were the one accepted for the poster. So here you see all these people listed. I'd like also to thank all the people that will help this afternoon, setting the environment, settings, and also being the tutor for the hands-on. So please also join me and applaud them. So yeah, that's it on my side. I was personally very thrilled to organize this event. We got 360 people registered. About 300 people joined this event on site, so I think the community responded to this call. So I'm personally very happy, and also ESA, Philab, we are all very happy about this sign that you sent to us. So I think the community is really working hard on foundation model. So I hope that there will be some other events in the future in that direction. I don't know if Raul is online, and as you may know, he couldn't make it. But still, he was one of the key elements for the organization of this event. So please, if you can say some few words. Thanks.
Hi, Nicholas. Thank you. I hope you guys can hear me.
Yeah, we do.
Okay, awesome. Clearly, it was a very productive meeting. Listening to the debriefs, I was having a major FOMO of missing out on the workshop, unfortunately. I think the results of this workshop will help us, the outcomes will help us understand where we are, where we need to go in the space on AI foundation models and AI in general. The outcomes will specifically help us understand where we need to seed new efforts and where we think we can help with collaboration so that we are not building siloed systems. We want to build capabilities that work across and benefit everyone. So with that note, I would really like to thank all the session chairs, the program committee members, as Nicholas was mentioning, for all the effort that went into planning and organizing this workshop. A special thank you to all my ESA colleagues for the amount of effort they've put in, specifically Nicholas in organizing this workshop. We couldn't really support him, unfortunately, given our situation. And finally, thank you to all of you for participating in this workshop. It's you who made this workshop a success. Thank you again.
Thank you. Very last word on my side, thanks as well the logistic guys that help, like the Regia, the canteen, the guys that mounted the tent and everything. So there's actually many people that helped to organize this event. So thanks a lot to them. And with that, on my side, I wish you a very successful hands-on if you participate to it, and safely return to your place, and then see you soon. Thanks a lot.